Do you know what keeps some scientists awake at night? Not black holes, not dark matter, not even the possibility of alien life visiting Earth. What haunts them is a question so simple, so obvious that nobody thought to ask it until 2018. A question that once asked cannot be unasked. A question that threatens everything we believe about being first on this planet. What if we are not the first intelligent species Earth has produced? What if, millions of years before the first human ever stood upright, another species looked at the stars and wondered the same things we wonder now? What if they built cities, developed technology, created civilization? And what if time erased almost every trace, leaving us convinced we were always alone? In 2018, two scientists sat down to write what would become one of the most unsettling scientific papers ever published. Dr. Adam Frank, an astrophysicist at the University of Rochester, and Dr. Gavin Schmidt, the director of NASA's Goddard Institute for Space Studies and one of the world's leading climate scientists. These were not fringe researchers chasing conspiracy theories. These were mainstream scientists with impeccable credentials, publishing in peer-reviewed journals respected by their colleagues. And they were about to ask a question that would make the entire scientific community profoundly uncomfortable. The conversation began innocently enough. Frank and Schmidt were discussing how to detect signs of ancient climate change in ice cores and sediment layers. They wanted to understand the markers that industrial civilizations leave behind: the carbon emissions, the chemical pollution, the atmospheric changes. This research had practical applications. It could help us understand our own impact on Earth's climate. It could help us identify similar industrial activity on distant exoplanets by analyzing their atmospheric composition. Standard climate science, nothing controversial. But then Schmidt asked a follow-up question that changed everything. If we are trying to understand what traces an industrial civilization leaves in the geological record, how long do those traces last? 10,000 years? A million years? What about 10 million years? What about 100 million years? Frank paused. He had not considered this timeline. Most climate research focuses on the recent past, the last few million years at most. Ice cores go back perhaps 800,000 years. Ocean sediment cores maybe a few million. But Schmidt was asking about deep time, geological timescales, and the more Frank thought about it, the more disturbing the question became. Because if they were trying to figure out how future scientists might detect our civilization millions of years from now, that implied another question. An obvious question that somehow nobody had systematically asked before. Could we detect a previous industrial civilization if one had existed millions of years in the past? The two scientists looked at each other. They both knew what this meant. They were about to propose something that would sound like science fiction. That would make headlines, that would provoke ridicule from some colleagues, but the science was sound. The question was legitimate, and once the idea took hold, they could not let it go. They decided to write a formal paper, not claiming that ancient civilizations existed, but asking whether we would be able to tell if they had, whether the absence of evidence actually meant anything. Whether our certainty that humans are Earth's first intelligent species was based on solid proof or just on assumptions we had never properly tested. They needed a name for this hypothesis, something memorable but not too sensational. Schmidt, a science fiction fan, suggested the Silurian hypothesis, named after a fictional reptilian species from the British television show Doctor Who. In the show, the Silurians were intelligent reptiles who ruled Earth millions of years before humans evolved, then went into hibernation deep underground, only to be awakened in the modern era. It was fiction, obviously, but it was fiction that asked the right question. What if intelligence on Earth was not a recent invention? What if it had happened before? The name was chosen with a touch of irony, a wink to the fact that they were asking something that sounded absurd. But the science behind the name was absolutely serious. In May 2018, the paper was published in the International Journal of Astrobiology, a legitimate peer-reviewed scientific journal. The title, The Silurian hypothesis: would it be possible to detect an industrial civilization in the geological record? Right from the opening paragraphs, Frank and Schmidt made their position clear. They were not claiming that ancient industrial civilizations existed. They were claiming something more subtle and more profound: that after sufficient time, geological and erosional processes would make it nearly impossible to detect such a civilization even if it had existed. That absence of evidence in this case genuinely was not evidence of absence, that we might be looking for the wrong things in the wrong places. And that our confidence in being first might be based on nothing more than the fact that we have not looked hard enough in the right ways. The reaction was immediate. Science journalists jumped on the story. Headlines appeared: "Scientists ask if dinosaurs had civilization." Were we Earth's first industrial species? The hypothesis that could rewrite history. Some coverage was thoughtful and accurate, but much of it sensationalized the idea, making it sound like Frank and Schmidt were claiming proof of ancient alien reptiles. The scientists had to repeatedly clarify. This was a thought experiment, a way of understanding what traces civilizations leave and how long those traces persist. Not a claim that dinosaurs built cities, but the damage was done. In the public mind, the Silurian hypothesis became associated with wild speculation rather than rigorous science. The academic response was more nuanced but equally uncomfortable. Most scientists praised the thought experiment as intellectually interesting. A good way to think about biosignatures on exoplanets. A useful framework for understanding our own civilization's long-term geological impact. But very few were willing to seriously entertain the possibility that it might actually be true. That somewhere in Earth's deep past, an industrial civilization might have risen and fallen, leaving traces so faint that we have simply never noticed them. Because accepting that possibility required accepting something much more unsettling. That we might not be special. That intelligence might not be unique to humans. That the story we tell ourselves about being the pinnacle of evolution, the first species to truly master this planet, might be wrong. But here is the thing about good scientific questions. Once asked, they do not go away just because the answers are uncomfortable. And the more you think about the Silurian hypothesis, the more you realize how little we actually know about deep time, how few assumptions we have really tested. How much of our certainty is based on the absence of evidence rather than evidence of absence. So let us think about this properly. Let us look at the numbers. Let us examine the timeline. Let us ask seriously and carefully whether an industrial civilization could have existed on Earth before humans, and whether, if it did, we would have any way of knowing. Earth is 4-5 billion years old. Complex life appeared in the oceans approximately 600 million years ago. Life moved onto land around 400 million years ago. For the next 400 million years, Earth was dominated by species that were not human. Dinosaurs ruled for 165 million years, from about 230 million years ago until their extinction 66 million years ago. That is 165 million years of dominance. Compare that to humans. Anatomically modern humans appeared roughly 300,000 years ago. Agriculture and settled civilization emerged about 10,000 years ago. Industrial civilization, the kind that burns fossil fuels and builds factories and leaves chemical signatures in the atmosphere, has existed for only about 300 years. Do you see the problem? We are comparing 300 years of human industrial activity to 165 million years of dinosaur existence. The ratio is staggering. Our entire industrial civilization represents 0. 2 of the time dinosaurs ruled Earth. If you compressed Earth's 4-5 billion year history into a single 24-hour day, dinosaurs would dominate for about 52 minutes. Human industrial civilization would last for less than 1/10 of 1 second, a literal blink. And in that blink we have completely transformed the planet's atmosphere, caused a mass extinction event, and left chemical traces that will persist in the geological record for millions of years. Now imagine those 52 minutes of dinosaur time, 165 million years, an almost incomprehensible span. Human civilization has existed for 10,000 years, and we have gone from stone tools to space stations. What could happen in 165 million years? How many times could intelligence evolve, civilizations rise and fall, technologies develop and be lost? The mind recoils from the scale, but the math is clear. There was time, plenty of time, more than enough time for something to happen that we have never considered. But time alone does not answer the question. Time creates a different problem, the problem of preservation, or rather the problem of erasure. Consider what happens to human artifacts over time. A wooden building rots away in decades or centuries. Steel corrodes. Iron rusts completely within tens of thousands of years. Even our most durable materials break down. Concrete crumbles. Glass, though chemically stable, shatters and weathers back into sand over millions of years. Plastics, our newest invention, break down into microplastics and eventually degrade through exposure to ultraviolet light and chemical processes. Current estimates suggest most plastics would be completely gone within 1 to 10 million years, and that is just the material decay. Then come the geological processes. Erosion wears away surfaces at a rate of approximately 1 centimeter per 1,000 years. Mountains rise and fall. Tectonic plates collide, subduct, recycle. The ocean floor, where much sediment accumulates, is completely recycled every 180 to 200 million years as it gets pushed under continental plates and melted in the mantle. Ice ages come and go, glaciers grinding across continents, scouring surfaces, depositing new sediments. Climate changes. Sea levels rise and fall. Areas that were once dry land become ocean floor. Areas that were ocean become mountains. After 66 million years, the time since the dinosaurs went extinct, these processes have reshaped Earth's surface almost beyond recognition. The continents have moved. India has crashed into Asia, creating the Himalayas. The Atlantic Ocean has widened. Entire mountain ranges have eroded away. And any artifacts, any buildings, any trace of surface civilization from that time would be long gone. Not just decayed, gone. Crushed, melted, eroded, scattered, transformed into unrecognizable minerals distributed through layers of rock that have themselves been compressed, heated, folded, and metamorphosed beyond their original state. This is why Frank and Schmidt's question is so profound. We look for dinosaur bones and we find them sometimes. Fossilization is rare, requiring perfect conditions. Rapid burial in fine sediment. Absence of oxygen to prevent decay, no scavengers, stable geology for millions of years so the fossil is not destroyed by heat, pressure, or erosion. Less than 1% of all species that ever lived left any fossils at all. The fossil record is not a complete library of Earth's history. It is a collection of lottery winners. Species that got extraordinarily lucky in death, and we extrapolate from these rare survivors to understand the past. But here is the critical point. Industrial civilizations do not fossilize the way bones do. Cities do not turn into fossils. Roads do not fossilize. Factories, power plants, computers, none of these things create the kind of remains that persist for 66 million years in recognizable form. Instead, they leave different traces. Chemical traces, changes in atmospheric composition, isotope ratios in sediment layers, concentrations of rare elements from mining, synthetic molecules that do not occur naturally. These are the signatures we should look for, but we are not looking, because we do not expect to find them. Because the paradigm says they should not be there, and this brings us to the most uncomfortable part of the hypothesis. The realization that our certainty about being first is based almost entirely on the absence of evidence. We have not found buildings from 66 million years ago, therefore no buildings existed. We have not found dinosaur tools, therefore dinosaurs did not use tools. We have not found clear chemical signatures of industrial activity in Cretaceous rocks, therefore no industry existed. But this logic only works if we have actually looked hard enough in the right places with the right methods, and we have not. The percentage of Earth's geological layers that have been examined for industrial chemical signatures is effectively zero. Most drilling is done for oil, minerals, or climate data. Not for traces of previous civilizations. Sample sizes are absurdly small. We have examined less than 1/100% of Earth's sedimentary rock for any purpose. And even within that tiny sample, we are not screening for industrial markers from deep time because the paradigm says it would be a waste of resources. Imagine examining 5 grains of sand from the entire Sahara Desert, finding no diamonds, and concluding with certainty that diamonds do not exist anywhere in the Sahara. That is roughly the level of sampling we have done of Earth's geological record when it comes to looking for traces of ancient industrial civilizations. And based on that infinitesimal sample size, we have concluded that we are definitely the first, the only, the unique intelligent species Earth has ever produced. That conclusion may be correct, but it is not proven, not even close. And the more you understand about deep time, about preservation, about the limits of fossilization and the processes that erase evidence, the more you realize that we are operating on assumptions that have never been properly tested. We believe we are first because we have always believed we are first, because the narrative of human exceptionalism is comforting, because the alternative is unsettling, but belief is not evidence. And absence of evidence after 66 million years of geological transformation means almost nothing. So the question remains, not proven, not answered, but asked, hanging in the air like the smoke from a fire that burned too long ago to see but might have left invisible traces in the ash. What if dinosaurs built a civilization before humans existed? What if intelligence on Earth is not a recent invention but an old pattern that is repeated before? What if we are not the first minds to wonder about our place in the universe? And if that is possible, if it cannot be ruled out, what does it mean for how we understand ourselves, our history, our future? Because if they existed and then disappeared, erased by time and catastrophe until almost nothing remained, what does that say about our own permanence? About the traces we will leave? About whether anyone will remember us 66 million years from now when we too have become compressed into thin layers of rock that future geologists might drill through without ever knowing we were here? The Silurian hypothesis is not just about dinosaurs. It is about time. About how time erases everything if given long enough. About how certainty becomes impossible across geological timescales. About how the question of whether we are first or latest can never be fully answered because the evidence we would need might not exist anymore. And about how we should think about our own civilization differently if we acknowledge that intelligence might be older than we thought, that we might be walking in footsteps we can no longer see, that the story of consciousness on Earth might be longer and stranger and more tragic than we have ever allowed ourselves to imagine. Before we continue this journey 100 million years into the past, exploring whether dinosaurs could have been intelligent, what traces they might have left, and while we might never find definitive proof either way, take a moment. If this question unsettles you, you are not alone. If it makes you wonder whether everything you learned about human uniqueness might be wrong, that is exactly the point. Hit the like button if you have ever questioned whether we are truly Earth's first intelligent species. Subscribe because this journey gets stranger with every minute, and the implications reach far beyond dinosaurs into questions about our own survival and what we will leave behind. And comment where you are listening from and whether this idea terrifies you or fascinates you, because understanding how you react to this question tells you something important about yourself and about the assumptions you carry about humanity's place in the vast sweep of deep time. The question has been asked. The paper has been published. The hypothesis exists. And now we must follow it wherever it leads, into the depths of the Cretaceous period, into the lives of creatures that might have been more than we ever imagined, into the evidence that might exist or might be forever lost, and ultimately into the mirror that this question holds up to our own civilization. Because asking whether dinosaurs built cities is really asking something else. Asking whether we will be remembered. Whether intelligence matters, whether consciousness is rare or common, Whether we are alone in time or just the latest in a long line of minds that emerged, wondered, built, and ultimately disappeared into the geological silence that claims everything eventually. The question has been asked, and now we search for answers, knowing we might never find them but searching anyway, because that is what intelligence does. It asks questions into the void and listens for echoes. Even when the echoes come from 66 million years away, even when they might not come at all. The question seems absurd at first. Dinosaurs, intelligent. We grew up with images of lumbering giants, tiny-brained reptiles operating purely on instinct. The Tyrannosaurus rex, terrifying but stupid. The long-necked sauropods, massive bodies with brains the size of walnuts. This is what popular culture taught us. This is what we believed. But what if almost everything we think we know about dinosaur intelligence is based on outdated science, incomplete evidence, and assumptions we never properly tested? What if some dinosaurs were not just smart for reptiles, but genuinely intelligent? Not human level perhaps, but approaching it. And what if the evidence has been sitting in museum drawers for decades, largely ignored because it contradicted the narrative we wanted to believe? To understand whether dinosaurs could have built civilizations, we must first understand what intelligence actually requires. Not in the abstract philosophical sense, but in the practical biological sense. What ingredients does evolution need to produce a species capable of complex thought, tool use, social organization, and technological development? Scientists have identified 5 key factors that appear necessary, though perhaps not sufficient, for intelligence to emerge. First, manipulators. Hands, tentacles, trunks, something that allows fine motor control and the ability to grasp and manipulate objects. You cannot build tools if you cannot hold things. Second, social complexity. Intelligence often evolves in species with intricate social structures where individuals must navigate relationships, cooperate, compete, and communicate. Third, free energy. Surplus food and time not spent on immediate survival. A species whose every waking moment is consumed by finding the next meal has no evolutionary pressure toward abstract thinking. Fourth, communication. Some way to share information between individuals, to teach and learn, to transmit knowledge across generations. And fifth, longevity. Long-lived individuals who have time to accumulate knowledge and pass it on to the young. Now here is the interesting part, the uncomfortable part. When you look at dinosaurs through this framework, when you actually examine the fossil evidence rather than relying on outdated assumptions, you discover something remarkable. Many dinosaur species had all 5 of these factors. Not all dinosaurs, obviously. The giant sauropods like Brachiosaurus were probably not candidates for intelligence. Too large brains, too small relative to their massive bodies, evolutionary pressure favoring size for defense rather than cognition. But smaller dinosaurs, particularly certain theropods, the 2-legged carnivorous dinosaurs, show evidence of every single prerequisite for intelligence. Let us start with manipulators. The famous velociraptor, made popular by Jurassic Park, had 3-fingered hands with an opposable digit. Not as dexterous as human hands, but far more capable than the claws of modern reptiles. Fossil evidence shows these hands could grasp, could hold objects, could manipulate prey with precision. Deinonychus, a related species, shows even more sophisticated hand structure. The joints allowed rotation, allowed the kind of fine motor control you would need for tool use. And then there is Troodon, small, bipedal, approximately the size of a large turkey or small human. Troodon's hands were remarkable. 3 fingers with an opposable thumb-like digit. Fossil analysis shows the musculature would have allowed a precision grip. The kind of grip you need to hold a stick, a rock, something that could be shaped into a tool. Social complexity is harder to prove from fossils, but we have clues. Fossilized trackways show that some carnivorous dinosaurs traveled in packs. Not just walking in the same direction by coincidence, but coordinated movement suggesting cooperative hunting. Velociraptor fossils have been found in groups suggesting pack behavior. Deinonychus fossils found near a single Tenontosaurus carcass, multiple predators apparently killed while attacking larger prey, evidence of coordinated group hunting. More intriguingly, fossilized nesting sites show that some dinosaur species engaged in communal nesting. Maiasaura duck-billed dinosaurs created nesting colonies where dozens of individuals laid eggs in close proximity and apparently cared for the young collectively. This kind of behavior, group child-rearing and cooperative parenting, is associated with high social intelligence in modern species. It requires recognizing individuals, maintaining relationships, coordinating care. It requires communication and trust. Free energy is perhaps the easiest factor to demonstrate. Many herbivorous dinosaurs lived in environments with abundant plant life. During the Mesozoic era, the climate was generally warmer and more humid than today. Plants grew prolifically. A large herbivore could spend less time foraging than modern equivalents because food was everywhere. This freed up time that could be used for social interaction, for exploration, for behaviors beyond immediate survival. Carnivores, meanwhile, while needing to hunt, often hunted in groups, as we discussed. Successful group hunts provide more food than a single predator can consume immediately, creating surplus. Surplus means leisure time. Leisure time creates evolutionary space for intelligence to develop because individuals with better problem-solving skills, better communication, better social navigation would have advantages in utilizing that free time productively. Communication is where things get truly fascinating. Sound does not fossilize. We have no direct evidence of dinosaur vocalizations, but we have indirect evidence that is extraordinarily suggestive. Many dinosaurs had hollow bones, particularly in the skull and neck regions. Hollow bones in modern birds, which are direct descendants of dinosaurs, create resonance chambers that allow complex vocalizations. Parasaurolophus, a duck-billed dinosaur, had an elaborate hollow crest on its head that paleontologists have reconstructed to understand its acoustic properties. When you blow air through a replica of this crest, it produces deep, resonant sounds that could carry for miles. This was not for defense. This was for communication, long-distance signaling across the landscape, potentially even individual recognition, different patterns of sound identifying different creatures. But the most compelling evidence comes from studying the inner ear structure preserved in some skulls. The cochlea, the part of the ear that processes sound, shows remarkable complexity in some species. Troodon's inner ear structure suggests it could hear a wide range of frequencies, particularly in the range that would be useful for vocal communication, not just detecting predators or prey, but actually listening to complex sounds and distinguishing subtle variations. The kind of hearing you need if you're going to have a complex vocal language. Modern parrots have similar ear structures, and parrots can learn hundreds of words, mimic complex sounds, and use vocalizations contextually. If Troodon had similar capabilities and the fossil evidence suggests it might have, then vocal communication sophisticated enough for cultural transmission of information was absolutely possible. Longevity completes the picture. How long did dinosaurs live? For a long time, we did not know. But advances in bone analysis, particularly studying growth rings in fossilized bones similar to tree rings, have given us estimates. Large dinosaurs like sauropods probably lived 80 to 100 years or more. Smaller species had shorter lifespans but still substantial. Troodon, based on bone ring analysis, likely lived 20 to 30 years. That may not sound like much compared to human lifespans of 70 to 80 years. But it is plenty of time for learning, for accumulating knowledge, for teaching offspring. Modern crows live only 10 to 15 years in the wild, yet they demonstrate remarkable intelligence, tool use, problem solving, and cultural transmission of learned behaviors. If a crow can develop culture in 15 years, what could a species with 30-year lifespans accomplish across thousands of generations? So the ingredients were there. Manipulative hands, social complexity, surplus energy, communication capacity, sufficient longevity, all 5 factors present in multiple dinosaur species, but ingredients are not the same as the meal. Possessing the prerequisites for intelligence does not mean intelligence actually evolved. So we must look at the direct evidence, we must look at brains. Here we encounter a fundamental problem. Brains do not fossilize. Soft tissue decays rapidly after death. What we have are skulls, hollow bone chambers where brains once resided. From these cavities, paleontologists can create endocasts, models showing the approximate shape and size of the brain. And from these endocasts, we can calculate something called the encephalization quotient, or EQ. This is the ratio of actual brain size to expected brain size for an animal of that body mass. It accounts for the fact that larger animals naturally have larger brains just to control their bodies. EQ measures how much brain an animal has above and beyond what is needed for basic bodily functions. That extra brain capacity is what allows for intelligence. Modern humans have an EQ of approximately 7, the highest of any known species. Dolphins have an EQ around 4 to 5. Great apes, chimpanzees, and gorillas have an EQ around 2.5 to 3. Dogs are around 1 to. Most reptiles, modern lizards, and snakes have an EQ of 0.5 to 1. Now here is where it gets interesting. Most dinosaurs, the large famous ones, had EQs similar to modern reptiles. T-Rex, despite its massive skull, had a brain only about the size of a human brain but a body weighing 8 tons. Its EQ was probably around 2, comparable to some birds but not exceptional. Sauropods were even lower, EQs below 1, huge bodies with relatively tiny brains. But Troodon was different, very different. When paleontologist Dale Russell analyzed Troodon's skulls in the 1980s, he discovered something that did not fit the dinosaur pattern at all. Troodon had a brain-to-body ratio higher than any other dinosaur, substantially higher. Its encephalization quotient was calculated at approximately 5.8. Higher than dolphins, approaching great apes. In a creature that lived 75 million years ago during the late Cretaceous period, evolution had produced a dinosaur with brain capacity rivaling some of the most intelligent animals alive today. Let that sink in for a moment. 75 million years ago, before the asteroid, before the mass extinction, before mammals had any chance to diversify and fill ecological niches, there was a dinosaur with dolphin-level intelligence wandering the forests of what is now North America. Troodon was not large, about 6 feet long from nose to tail, weighing maybe 100 pounds, roughly the size of a large dog. It walked upright on 2 legs, freeing its arms for grasping. It had large eyes positioned forward on the skull, providing stereoscopic vision and depth perception, critical for judging distances when using tools or manipulating objects. Its hands, as we discussed, were capable of precision grips, and its brain was massive relative to its body size. This was not a stupid animal. This was not an instinct-driven reptile. This was a creature with genuine cognitive capacity. The kind of capacity that, in the right environment with the right evolutionary pressures, could potentially develop further. But here is where the story takes a turn that many scientists still find uncomfortable. In 1982, Dale Russell published not just his analysis of Troodon's intelligence, but a thought experiment that has haunted paleontology ever since. He asked a simple question: what if the asteroid had not hit? What if Troodon and its descendants had continued evolving for another 66 million years instead of going extinct? Where might that evolutionary path have led? Russell created a life-sized model based on extrapolating evolutionary trends. He assumed that brain size would continue increasing because intelligence was proving adaptive for Troodon's ecological niche. He assumed upright posture would become more pronounced because bipedalism was already established. He assumed hands would become more dexterous because tool use, even if only manipulating prey, was selecting for better fine motor control. The result was a creature he called the dinosaur. Bipedal, standing about 5 feet tall, with a large bulbous head to accommodate an even bigger brain, 3-fingered hands with fully opposable thumbs, and a body plan that looked eerily, disturbingly humanoid. The model was displayed in the Canadian Museum of Nature in Ottawa and immediately sparked controversy. Critics accused Russell of anthropocentrism, of making dinosaurs look human because that is what we expect intelligent creatures to look like, of projecting human evolution onto an entirely different lineage. But Russell defended his work by pointing to something called convergent evolution. This is when different species, evolving in similar environments under similar pressures, independently develop similar solutions. Wings evolved separately in insects, pterosaurs, birds, and bats because flight imposes certain physical requirements that lead to similar structures. Eyes evolved independently dozens of times in different lineages because vision is so advantageous that evolution keeps reinventing it. Russell argued that intelligence also has certain physical requirements that lead to convergent solutions. You need a large brain, which means a large skull. You need manipulators, which means hands or tentacles. You need good sensory input, which means forward-facing eyes for depth perception. You need to free your manipulators from locomotion, which means either multiple limbs like an octopus or upright bipedal posture like humans and birds. These are not arbitrary human features. They are functional requirements for intelligence. And if intelligence was adaptive for Troodon's descendants, evolution would keep selecting for improvements in these areas, leading naturally toward the dinosaurid body plan regardless of human evolution. Whether Russell was right or wrong about the specifics, his thought experiment made one thing clear: there was nothing inherently impossible about dinosaur intelligence. The dinosaurid was not proof that intelligent dinosaurs existed, but it was proof that they could have existed. That the evolutionary potential was there. That given enough time and the right environmental pressures, dinosaurs could have become smart. Very smart, potentially as smart as us. But we do not need to speculate about hypothetical dinosaurids to know that dinosaurs were capable of remarkable intelligence. Because some dinosaurs survived the extinction. We call them birds. And birds, despite having small brains optimized for flight, demonstrate cognitive abilities that shame the old stereotype of dinosaurs as stupid reptiles. Crows are dinosaurs, direct descendants of theropods, the same group that included Velociraptor and Troodon. And crows are astonishingly intelligent. New Caledonian crows craft tools from twigs, shaping them into hooks to extract insects from tree bark. They make multiple different tool types for different purposes. They store tools for later use. They teach their young how to make tools, passing knowledge across generations. This is cultural transmission of technology. Crows can solve multi-step puzzles that require planning ahead. They understand water displacement, dropping stones into tubes to raise water levels and access floating food, demonstrating understanding of basic physics. They recognize individual human faces and remember them for years. They even hold grudges, attacking people who previously threatened them while ignoring others. African gray parrots, also dinosaurs, also theropod descendants, demonstrate even more sophisticated cognition. Alex, the famous African gray studied by researcher Irene Pepperberg, learned over 100 words, but he did not just mimic sounds, he understood concepts. He could identify colors, shapes, materials. He could count to 6. He understood same and different. He could answer questions about objects he had never seen before by combining known categories. When shown a blue wooden triangle and asked what shape, what color, what material, he answered correctly for each. He could refuse to participate in experiments, saying, "Wanna go back when tired." And on the last night of his life, his final words to Pepperberg were, "You be good, I love you." Not random mimicry. Contextual, emotional communication. Ravens demonstrate theory of mind, the ability to understand what others know or do not know. They hide food caches, and if they notice another raven watching, they return later to move the food to a new hiding spot. They understand that the observer now knows the location and will steal the food. This is not instinct. This is genuine understanding of other minds, of perspective-taking, of deception. It is cognitive ability we once thought was unique to great apes and humans. These are birds, flying animals with brains limited in size by the energy cost of flight. Their entire bodies are optimized for being lightweight, yet they achieve this level of intelligence with brains weighing only a few grams. Now imagine what could be achieved by a ground-dwelling dinosaur with no flight weight restrictions. A dinosaur that could afford to have a brain 10 times larger because it did not need to lift that weight into the air. A dinosaur like Troodon with its already exceptional brain-to-body ratio. Given millions of years of continued evolution, selecting for even greater intelligence, where might that path have led? The fossil record shows us that the evolutionary trajectory existed, that dinosaurs were not locked into being stupid, that some lineages were actively trending toward greater intelligence. Troodon at 75 million years ago had already reached dolphin-level cognition. Who knows what other species we have not found? Intelligence often evolves in smaller animals with specialized niches. These species tend to have smaller populations, more limited geographic ranges, exactly the kind of species least likely to fossilize. We have found perhaps 1 to 2% of all dinosaur species that ever existed. The fossil record is overwhelmingly biased toward large, abundant animals that lived in environments conducive to fossilization. Rare, intelligent species living in upland forests or other environments where fossilization is unlikely might leave no trace at all. So here is what we know. We know that multiple dinosaur species had all 5 prerequisites for intelligence. We know that at least one species, Troodon, achieved brain-to-body ratios comparable to dolphins. We know that dinosaur descendants, birds, demonstrate remarkable cognitive abilities despite brain size limitations. We know that convergent evolution tends to produce similar solutions for intelligence across different lineages. And we know that dinosaurs had 165 million years to evolve, a timescale so vast that intelligence could have emerged, flourished, and gone extinct multiple times without us ever finding evidence. What we do not know, what we may never know, is whether any dinosaur species actually crossed the threshold from intelligent animal to civilization-building species, whether any of them developed language complex enough for abstract thought, whether any of them invented tools and passed that knowledge down across generations, whether any of them organized into societies larger than family groups or hunting packs, whether any of them built structures, created art, wondered about the stars. The absence of evidence is not evidence of absence, but it is also not evidence of presence. We are left with a question that cannot be answered definitively, a question that hangs in the space between possible and proven. Intelligence was possible. The ingredients existed. The evolutionary trajectory existed. But did it actually happen? And that is perhaps the most unsettling realization of all, that we genuinely do not know. That after 2 centuries of paleontology, after thousands of fossil discoveries, after all our scientific advances, we cannot rule out the possibility that 100 million years ago, an intelligent dinosaur stood where you are standing now and wondered the same things you wonder. Whether they were alone, whether intelligence had meaning, whether anything they built would survive them. And if they did exist, if they did build and wonder and question, time has erased them so thoroughly that we can only speculate, can only ask, can only imagine the shadows of minds that might have been living and thinking and ultimately disappearing into the geological silence that claims everything eventually. The question of whether they were intelligent is not fully answered, but the question of whether they could have been, that answer is yes, uncomfortably, undeniably yes. Imagine you are standing in the ruins of New York City, not today, not tomorrow, but 66 million years from now. The year 66,000,2025 AD. The skyscrapers are gone, the Empire State Building, the Brooklyn Bridge, the subway system, all of it vanished. Where steel towers once pierced the sky, there are now rolling hills covered in whatever vegetation has evolved to thrive in Earth's changed climate. Where millions of people once lived and worked and dreamed, there is nothing, no trace, no sign that humanity ever existed at all. Would a geologist from that distant future drilling core samples through the rock layers find anything to prove that an industrial civilization once flourished here? Would they find our cities, our technology, our plastics and concrete and steel, or would they drill right through the thin layer that represents our entire existence without ever knowing we were here? This is not science fiction. This is physics. This is chemistry. This is the simple, terrifying reality of what time does to everything. And understanding this reality is essential to understanding whether we could ever detect a dinosaur civilization if one had existed. Because the question is not just whether dinosaurs built cities. The question is whether cities can survive 66 million years in any recognizable form. And the answer, according to every geologist who has studied deep time preservation, is almost certainly no. Not cities, not buildings, not artifacts. Not anything we would traditionally think of as archaeological evidence. Which means if we are going to search for traces of dinosaur civilization, we need to completely rethink what traces actually means. Let us start with the materials humans use to build our world and calculate how long they last. Wood, one of our oldest building materials, begins rotting almost immediately after a tree dies. Bacteria, fungi, insects all attack the cellulose and lignin that give wood its structure. In a temperate climate with moisture, an untreated wooden structure will be unrecognizable within a few hundred years. Even in dry deserts where preservation is better, wood breaks down chemically over thousands of years, crumbling into powder that blows away with the wind. After 10,000 years, essentially no wood remains intact. After 100,000 years, even the chemical signature of ancient wood is mostly gone. After 1,000,000 years, nothing. And we are talking about surviving 66 million years. Wood does not make it past the first 15% of that time scale. Steel, the backbone of modern civilization, our bridges and buildings and vehicles, lasts longer but not much longer. Iron oxidizes. Rust is not just surface corrosion. It is the actual transformation of metallic iron back into iron oxide, the mineral form it came from before we smelted it. In humid environments, steel structures rust through completely in decades to centuries. Even in dry conditions, even buried underground away from oxygen and water, steel does not last. Over thousands of years, it corrodes away. Over tens of thousands of years, it becomes unrecognizable lumps of rust. Over hundreds of thousands of years, even those lumps break down and disperse. After 1,000,000 years, the iron has returned completely to oxidized mineral forms scattered through the soil. There is no way to look at that dispersed iron and know it was once a skyscraper or a car. It looks identical to natural iron deposits. Concrete, which we use for everything from sidewalks to dams to entire cities, breaks down through a process called carbonation. Carbon dioxide from the air slowly penetrates the concrete, reacting with the calcium compounds that give concrete its strength, turning them into calcium carbonate, basically limestone. This makes the concrete weaker, more porous, more vulnerable to water infiltration and freeze-thaw cycles. A concrete structure might last thousands of years if conditions are favorable. Maybe tens of thousands, but not millions. Geological forces take over. Tectonic activity creates stresses that crack the concrete. Erosion wears it away. Heat and pressure from being buried under accumulating sediments transform it chemically. After 1,000,000 years, concrete has returned to something chemically similar to the limestone and clay it was made from, compressed into rock layers indistinguishable from natural sedimentary formations. Plastic, our newest invention, the material we have created in such vast quantities that we have fundamentally altered Earth's surface chemistry, breaks down more slowly than we once thought but still breaks down. Ultraviolet radiation from sunlight breaks the long polymer chains into shorter fragments. Mechanical action, waves on a beach or wind-blown sand, grinds plastic into smaller and smaller particles. Bacteria, which are evolving right now to digest plastics, accelerate chemical decomposition. Current estimates suggest most plastics will be completely degraded within 1 to 10 million years. They will break down into their component molecules, which will disperse into the environment, become part of the carbon cycle, and disappear. After 66 million years, the vast ocean of plastic we are creating today will be gone, completely gone. Maybe, unusual concentrations of certain synthetic polymers might be detectable in sediment layers if you knew exactly what to look for and where to look. But there will be no plastic bottles, no bags, no identifiable artifacts, just chemical anomalies that could easily be dismissed as natural processes. Even glass, one of the most chemically stable materials we create, does not survive indefinitely. Glass is basically melted sand, silicon dioxide, the same stuff that makes up much of Earth's crust. Given enough time, glass returns to sand. It weathers, cracks, breaks down. Ancient glass artifacts from Roman times, only 2,000 years old, are already showing significant degradation. After millions of years, glass becomes sand again. You cannot look at a beach and determine which grains were once bottles and which were always just sand. The chemistry is identical. So everything we build, everything we make, everything physical about our civilization disappears given enough time. This is not speculation. This is observed fact. We can watch these processes happening. We can measure decay rates. We can calculate how long things last. And those calculations tell us that after 66 million years, essentially nothing remains. The Manhattan skyline becomes a thin layer of unusual mineral concentrations in sedimentary rock. And even that layer gets compressed, heated, folded, eroded, and scattered until there is nothing left to distinguish it from any other rock layer formed under any other set of natural conditions. But material decay is only the first problem. The second problem is geological transformation. Earth's surface does not sit still. It moves, it changes, it churns. Tectonic plates drift at rates of a few centimeters per year. That does not sound like much. But over 66 million years, continents move thousands of kilometers. India crashes into Asia, creating the Himalayan mountain range. The Atlantic Ocean widens. The Pacific Ocean shrinks. Entire ocean floors get pushed under continental plates in subduction zones, melting back into the mantle. The ocean floor is completely recycled every 180 to 200 million years. If a dinosaur civilization built coastal cities, as most civilizations do because access to water and trade routes makes coasts attractive, those cities are now either on the bottom of the ocean floor or they have been subducted into the mantle and melted. Either way, gone. Completely, irrecoverably gone. On continents, erosion is the great eraser. Rain wears away rock at a rate of about 1 centimeter per 1,000 years on average. That is 660 meters of erosion over 66 million years, 2,000 feet of rock surface removed by rain and wind and ice. Any structure on the surface would be worn away long before that process completed, but even buried structures do not escape. As erosion removes surface layers, everything underneath gets compressed by the weight of accumulating sediment above. The weight transforms rock through a process called metamorphism. Sedimentary rock, the kind that might preserve fossils or chemical traces, gets heated and compressed and transformed into metamorphic rock. Limestone becomes marble. Sandstone becomes quartzite, and in that transformation, fine details are lost. Chemical signatures blur. The rock remembers that it was sediment, but it no longer preserves the specific chemistry of what happened when that sediment was deposited. Ice ages add another layer of erasure. Over the past few million years, massive glaciers have repeatedly advanced and retreated across much of the northern hemisphere. Glaciers are like planet-sized grinding wheels. As they move, they scour the surface, removing everything down to bedrock. The Great Lakes in North America were carved by glaciers. The entire topography of Canada and Scandinavia was shaped by ice sheets up to 2 miles thick grinding across the landscape. Any trace of previous civilizations in those regions would be scraped away, pulverized into rock flour, and deposited somewhere else as unrecognizable sediment. Then there is the simple fact that most of Earth's surface from 66 million years ago is no longer accessible. Some has been buried under kilometers of newer sediment. Some has been pushed deep into the crust where heat and pressure have transformed it beyond recognition. Some has been eroded away completely. The percentage of Earth's surface that is both from the right time period and exposed or accessible enough to examine is astonishingly small. And within that tiny fraction, we have sampled even less. Most geological drilling is done for specific purposes. Looking for oil, looking for minerals, looking for groundwater, analyzing climate history from sediment cores. Nobody is systematically screening ancient rock layers for industrial chemical signatures because the paradigm says there is nothing to find. So we do not look. And not looking, we do not find. And not finding, we conclude nothing was there. A perfect circular logic that confirms itself. Given all this decay and transformation and erosion, what could possibly survive? What traces might persist for 66 million years? The answer is nothing direct but possibly indirect. Chemical signatures, isotope ratios, unusual element concentrations, things that require sophisticated analysis to detect and careful interpretation to understand. Carbon isotopes provide one possible signature. When plants photosynthesize, they preferentially absorb carbon-12 over carbon-13 because carbon-12 is slightly lighter and easier to incorporate into molecules. This means organic material, stuff made from plants or animals that ate plants, has a specific carbon isotope ratio that is different from inorganic carbon from volcanic sources or dissolved in the ocean. When we burn fossil fuels, coal and oil and gas that formed from ancient organic material, we release carbon into the atmosphere with that organic isotope signature. This changes the atmospheric carbon-13 to carbon-12 ratio in a distinctive way. That change gets preserved in sediments, in the shells of marine organisms, in any material that incorporates atmospheric carbon as it forms. Our industrial revolution, just 200 years of burning fossil fuels, has created a carbon isotope spike that will be detectable in sediment layers millions of years from now. It will be a thin layer, maybe just a few centimeters thick, representing a few thousand years of deposition. But it will be there, a chemical fingerprint of industrial activity. If a dinosaur civilization burned fossil fuels for energy, heating, metallurgy, or industry, they would create the same signature. A thin layer in the rock record where carbon isotope ratios shift suddenly toward organic sources, stay shifted for some period representing the duration of their industrial activity, then return to normal after the civilization collapsed or exhausted their fuel sources. Finding such a layer would be strongly suggestive of industrial activity, but here is the problem. Volcanic eruptions also release carbon with unusual isotope ratios. Massive releases of methane from melting permafrost or ocean floor clathrates also shift carbon isotopes. Natural processes can mimic industrial signatures. Distinguishing between them requires multiple lines of evidence, careful analysis, and luck in finding well-preserved sediments from the right time period. Nitrogen isotopes offer another potential marker. Industrial-scale agriculture requires fertilizers. Natural fertilizers like manure or artificial fertilizers like those we produce from atmospheric nitrogen through the Haber-Bosch process both change nitrogen isotope ratios in soils. Those changes can be preserved in sedimentary deposits if agricultural runoff reaches lakes or oceans where sediments accumulate. A civilization practicing intensive agriculture might leave a nitrogen isotope signature. But again, natural processes complicate interpretation. Algae blooms, volcanic activity, changes in ocean circulation all can affect nitrogen isotopes. You cannot point to a single anomalous reading and declare it evidence of civilization. You need patterns, multiple measurements, context. Rare earth elements provide a potentially more definitive signature. Modern electronics require rare earth metals like neodymium, dysprosium, and europium. These elements are called rare not because they do not exist, but because they are typically dispersed rather than concentrated. Mining and refining them creates unusual concentration patterns. If a dinosaur civilization used electronics, they might have mined rare earth elements, creating localized concentrations in their industrial sites. Those concentrations, if buried and preserved in sedimentary rock, might still be detectable as anomalies. Unusual concentrations of specific elements in specific ratios that do not match natural geological processes. But finding such a signature requires looking for it, requires drilling in the right place, requires analyzing samples for the right elements, and requires distinguishing artificial concentrations from the countless natural processes that also concentrate elements: volcanic hydrothermal vents, magma intrusions, metamorphic fluid flows. Synthetic molecules offer perhaps the clearest potential signature. Certain complex organic molecules do not occur naturally. PCBs, pesticides, pharmaceutical compounds, these are artificial creations that would never form through natural chemistry. If traces of such molecules were found in ancient sediments, it would be difficult to explain through natural processes. But synthetic molecules are also among the least likely things to survive 66 million years. Most break down chemically within thousands to millions of years. Maybe in oxygen-free sediments with the right chemistry, some fragments might persist longer, but it would require extraordinary preservation and extraordinary luck to find them. The most definitive signature would be radioactive isotopes that only exist through artificial processes. Plutonium-244, for example, does not occur naturally on Earth. It is only created in nuclear reactors or weapons. It has a half-life of 80 million years, which means after 66 million years, about half the original amount would still remain. If a dinosaur civilization developed nuclear technology, even if they used it only briefly, finding plutonium-244 in Cretaceous-era sediments would be absolute proof of technological activity. But here is the catch. Nobody is looking for plutonium in dinosaur-age rocks. Why would they? The paradigm says it should not be there. So sediment cores are analyzed for climate proxies, for fossil content, for mineral resources, but not for artificial radioactive isotopes. The sample might exist in a core sitting in storage somewhere, but unless someone specifically tests for plutonium-244, it will never be found. This brings us to the fundamental problem of searching for something you do not expect to find. Science operates on hypotheses. You propose that something might be true, then design experiments to test it. But if the dominant paradigm says something is impossible, nobody proposes the hypothesis, nobody designs the experiments, nobody allocates the funding. The Silurian hypothesis is elegant precisely because it exposes this gap. It asks, have we actually looked for evidence of ancient industrial civilizations? And the answer is no, we have not. Not systematically, not comprehensively, not with the specific intention of finding industrial chemical signatures in deep time. Frank and Schmidt pointed to one particular event that illustrates how difficult it would be to distinguish industrial from natural processes after millions of years. The Paleocene-Eocene thermal maximum, or PETM, which occurred 56 million years ago. This was a period of rapid global warming. Over approximately 20,000 years, global temperatures increased by 5 to 8 degrees Celsius. Carbon dioxide levels in the atmosphere spiked. Ocean acidification occurred. Deep sea species went extinct. And then, over the next 200,000 years, the climate gradually returned to normal. The mainstream explanation is that volcanic eruptions in the North Atlantic, massive basalt flows that created much of Greenland and Iceland, released enormous amounts of carbon dioxide. Or perhaps the warming triggered release of methane frozen in ocean sediments, creating a feedback loop. Natural causes, natural processes, but here is the unsettling question Frank and Schmidt raised. Could the PETM instead be the signature of an industrial civilization? The timescale fits: 20,000 years of rapid carbon release followed by gradual recovery. That is roughly what we would expect if a civilization developed industry, burned fossil fuels for 10 or 20,000 years, then collapsed, allowing natural processes to slowly remove the excess carbon from the atmosphere. The carbon isotope signatures from the PETM resemble fossil fuel burning. The climate effects match what industrial activity produces. If you showed a geologist from the future a sediment core from our current era and asked them to identify the Anthropocene, the age of humans, they would point to the exact same kind of signals we see in the PETM layer: carbon spike, temperature increase, ocean acidification, species extinction. Now, to be clear, most scientists think the PETM was natural. The amount of carbon released was enormous, probably requiring volcanic activity on a massive scale. And there is no other evidence of civilization from that time period. No synthetic molecules, no unusual element concentrations, no artificial isotopes. But the point is not that the PETM definitely was a civilization. The point is that we cannot tell for certain. After 56 million years, the signals are ambiguous. Natural and industrial processes create similar enough signatures that distinguishing between them requires multiple lines of evidence, most of which do not survive that long. And if we cannot confidently rule out industrial activity 56 million years ago where we have actually looked at the evidence, how can we confidently rule it out 95 million years ago or 120 million years ago where we have barely looked at all? The sample size problem cannot be overstated. Earth's sedimentary rock record spans billions of years. The total volume of sedimentary rock is almost incomprehensibly vast. And the percentage of that rock that has been sampled, drilled, analyzed, examined in any way is a fraction of a percent. Most sedimentary rock is buried deep underground or under the ocean. Inaccessible, unexamined. The portions we have accessed were accessed for specific purposes that had nothing to do with looking for ancient civilizations. We were looking for oil, for gold, for understanding past climates, for finding fossils. We were not screening for industrial chemical signatures because nobody thought to look. Imagine the entirety of human knowledge about Earth's geological history as a library. But instead of having access to the whole library, you are allowed to examine 5 random books out of 1,000,000. Based on those 5 books, you must determine everything that ever happened in that library over the past billion years. That is roughly the sampling situation we are in. And based on that absurdly limited sample, we have concluded with confidence that no industrial civilizations existed in deep time. Not because we found evidence of absence, but because we found an absence of evidence, which is a very different thing. So what would a proper search look like? It would require a coordinated global effort to sample sedimentary rocks from the Mesozoic era, the age of dinosaurs, systematically screening for anomalous chemical signatures. Carbon and nitrogen isotope spikes, unusual rare earth element concentrations, synthetic molecule fragments, artificial radioactive isotopes. The search would need to cover multiple continents, multiple rock types, multiple time periods, because we do not know when or where a civilization might have existed. It would require developing new analytical techniques to detect trace signatures that have degraded over tens of millions of years. It would cost conservatively $50 to $100 million over a decade. And it would require scientists willing to risk their reputations on a search that might find nothing. Currently, that funding does not exist. That willingness does not exist, because the paradigm says it would be a waste of resources. Because absence of evidence has been mistaken for evidence of absence. Because we are so certain we are first that we have never seriously tested whether that certainty is justified. And so the question remains unanswered. Not because it is unanswerable, but because we have chosen not to answer it. The traces might exist, buried in rocks we have never examined. Or they might not exist, erased by 66 million years of geological processes beyond any hope of recovery. We do not know which, and until we look properly we will not know. The stones keep their secrets, not because the secrets do not exist, but because we have never asked them the right questions in the right ways, and without asking, without looking, without testing, we remain in ignorance, certain of our uniqueness, confident in our primacy, convinced we are first. Based on nothing more than the fact that we have not found evidence we have never actually searched for. The absence of proof has become proof of absence, and that perhaps is the greatest illusion of all. 66 million years ago, on what began as an ordinary morning in the late Cretaceous period, something appeared in the sky that would end a world, not slowly, not gradually, but in a single day of fire and darkness that would erase 165 million years of evolutionary history in a geological eye blink. If intelligent dinosaurs existed, if they had built cities and developed technology and wondered about their place in the universe, they died that day. All of them. And everything they had created, everything they had learned, everything they had built, was obliterated so thoroughly that even if they had left messages, even if they had tried to preserve knowledge for whatever species might come after, the violence of that extinction event would have destroyed almost every trace. This was not just a mass extinction. This was planetary catastrophe on a scale that specifically perfectly ensured that any civilization existing at that moment would not just be killed but erased from history. The asteroid was approximately 10 kilometers in diameter, 6 miles across, small by cosmic standards. Jupiter's moon Europa is 3,100 kilometers in diameter. Earth itself is nearly 13,000 kilometers. This object was a grain of sand by comparison, but it was a grain of sand traveling at 20 kilometers per second, 45,000 miles per hour, and when something that massive moving that fast hits something solid, the physics become apocalyptic. The kinetic energy, the energy of motion, converts instantly into heat and shockwave. The calculation is straightforward. 1/2 times mass times velocity squared. The result is an energy release of approximately 100 million megatons. To put that in perspective, the atomic bomb dropped on Hiroshima released about 15 kilotons. This impact was equivalent to 2 billion Hiroshima bombs detonating simultaneously, not spread across the planet, concentrated in a single location, the Yucatan Peninsula. A place that is now Mexico but was then just another stretch of coastline on the supercontinent that dinosaurs called home. The moment of impact can be reconstructed with disturbing precision. Geologists have analyzed the crater, called Chicxulub after the town nearest its center. They have studied the ejecta layer, the debris thrown out by the impact. They have modeled the physics, run computer simulations, tested the scenarios against the physical evidence. And from all this we can describe what happened minute by minute, hour by hour, what it would have been like to be there, what any intelligent observer would have experienced, whether they understood what was happening or not, whether they had warning or not, whether they had time to be afraid or whether death came too fast for fear. At time zero, the instant of impact, the asteroid struck the shallow sea covering the Yucatan Peninsula at an angle of approximately 60 degrees from horizontal. This was, cruelly, the worst possible angle. A straight vertical impact would have thrown more debris straight up into space where it could never fall back. A shallow graze might have fragmented the asteroid, reducing the energy delivered to Earth, but 60 degrees was perfect for maximizing devastation. The asteroid punched through the water layer in less than a second. Water is nothing to an object moving that fast. Then it hit the limestone bedrock beneath. The rock did not crack or shatter, it vaporized, instantly converted from solid stone into superheated plasma. The asteroid itself vaporized. 6 miles of rock, gone in an instant, converted into a fireball expanding at supersonic speeds. Within the first second, a crater 30 kilometers wide and 20 kilometers deep had been excavated. But the crater did not stop growing. The shockwave propagated outward through the rock at thousands of meters per second, fracturing and ejecting material. Within 10 seconds, the crater was 100 kilometers wide. Within 30 seconds, it reached its maximum diameter of 180 kilometers, wider than the distance from New York City to Philadelphia, deep enough to hold Mount Everest with room to spare. And the material excavated from this crater, millions of cubic kilometers of vaporized and melted rock, was thrown upward and outward at velocities exceeding escape velocity. Some of it literally left Earth, flung into space by the violence of the impact. Most of it, too slow to escape but moving at thousands of kilometers per hour, arced up into the atmosphere and then began to fall back down. All around the planet, a global rain of molten rock. At ground zero, nothing survived. The Yucatan Peninsula and everything within 500 kilometers was simply gone. Vaporized, pulverized, erased. Any dinosaurs, any plants, any structures, if they existed, removed from existence in less time than it takes to blink. But the destruction did not stop at ground zero. The energy of the impact radiated outward as a shockwave traveling through Earth's crust. An earthquake, not the kind you experience when a fault line slips. This was an earthquake of magnitude 11 or higher, off the scale of any quake in human history. The ground rose and fell in waves like the surface of the ocean during a storm. Trees were ripped from the ground, mountains collapsed, and the shaking did not stop. It continued for hours, echoing and re-echoing around the planet as seismic waves circled the globe multiple times. The ocean, meanwhile, had been hit by the equivalent of the largest explosion in history occurring in the middle of a shallow sea. The water was displaced. Hundreds of cubic kilometers of water thrown outward in all directions, forming a wave. Not a wave like you see at the beach. A tsunami. The initial wave height was estimated at over 1 kilometer, 3,000 feet of water moving at the speed of a jet aircraft. This wave radiated outward from the impact site, crossing the Gulf of Mexico in minutes, hitting the coastlines of what would become the southern United States, Central America, and northern South America. The wave did not break and crash like normal waves. It simply arrived, a wall of water that kept coming, that pushed inland for hundreds of kilometers, that picked up everything in its path, forests and soil and anything living, and carried it all in a churning mass of destruction. When the water finally receded, pulled back by gravity toward the ocean, it left behind nothing but scoured bedrock and scattered debris. But the earthquake and tsunami, as catastrophic as they were only the beginning. The impact had thrown trillions of tons of material into the upper atmosphere, rock that had been vaporized, melted, or pulverized into dust. This debris cloud spread around the planet within hours, and as it spread, the larger pieces, rocks that had been melted and flung into the sky, began to fall back down, not just at the impact site. Everywhere, the entire planet became a shooting gallery. Meteors burning as they re-entered the atmosphere, lighting up the sky like a second sun. But unlike normal meteors that burn up completely, these were large enough to reach the ground. White-hot rocks the size of cars, houses, buildings, falling across every continent. And where they landed, they started fires. By the end of the first day, half the world was burning. The heat from re-entering debris had ignited forests from North America to Asia. Wildfires on a scale never seen before or since. The smoke rose into the already debris-choked atmosphere, adding soot to the dust. And then came the acid rain. The impact had vaporized limestone and sulfur-rich rocks. The sulfur combined with water vapor in the atmosphere to form sulfuric acid. It began to rain, not clean water, acid, falling across the planet, dissolving exposed minerals, killing plants that had somehow survived the fires, poisoning lakes and rivers. The rain fell for weeks, and when it finally stopped, the sky remained dark. The debris and smoke from the impact and fires had created a global cloud layer that blocked the sun. Scientists call this impact winter. The sunlight that reached the surface dropped to perhaps 1% of normal levels. Photosynthesis stopped. Not immediately, not everywhere at once, but within weeks plants began to die. Without sunlight they could not produce energy, they could not grow, the leaves fell, the small plants withered. And with the plants dying, the herbivores began to starve. Large herbivores, the sauropods and hadrosaurs that required hundreds of pounds of vegetation daily, died first. Within months, the great herds were gone, dead or dying, their bodies rotting where they fell, providing temporary food for scavengers and carnivores. But that food did not last. Within a year, the carnivores were starving too. Without herbivores to hunt, they turned on each other or simply succumbed to hunger. The ecosystems that had taken millions of years to evolve collapsed in a single generation. The darkness lasted for years. Some estimates suggest 5 years, others say 10. The uncertainty comes from not knowing exactly how much debris stayed suspended in the atmosphere versus how quickly it settled. But regardless of the exact duration, the result was the same: a world without sunlight. Temperatures plummeted, not everywhere uniformly. The equator remained warmer than the pole, but global average temperature dropped by 20 to 30 degrees Celsius. Areas that had been tropical became frozen. Ice formed in regions that had never seen ice. And in the darkness and cold, species after species went extinct. 75% of all species on Earth died, not over millions of years. Over thousands of years at most. A geological instant. The dinosaurs, the rulers of Earth for 165 million years, were gone, all of them, every single non-avian dinosaur species. The only survivors were small, burrowing mammals, some birds, crocodiles that could survive months without food, turtles that could hibernate, fish in deep ocean waters insulated from surface catastrophe, insects that could survive on detritus. The large, the dominant, the specialized, all dead. And if intelligent dinosaurs had existed, they died too, because intelligence does not protect you from planetary catastrophe. Intelligence does not let you photosynthesize in darkness. Intelligence does not keep you warm when global temperatures plummet. Intelligence might let you understand what is happening, might let you know that you are watching the end of your world, but it does not save you. This brings us to the most haunting question. Did they see it coming? If an intelligent species existed at the time of the impact, did they have any warning? We know modern humans did not detect asteroids until the 1800s, when telescopes became powerful enough to spot small objects moving against the background of stars. We did not start systematically tracking near-Earth asteroids until the 1990s. Even today, with all our technology, our catalog of potentially hazardous asteroids is incomplete. An object coming from the outer solar system, dark and cold and non-reflective like the Chicxulub impactor probably was, might not be detected until weeks or months before impact. Maybe only days. If a dinosaur civilization had telescopes, if they had been mapping the stars and tracking celestial objects, they might have seen the asteroid approaching. A point of light growing brighter night by night, moving against the background stars, coming closer. Some individual, some astronomer looking through a primitive telescope or simply watching the sky carefully might have calculated the trajectory, realized it was going to hit, tried to warn others. But what could they do? They had no space program, no way to deflect an asteroid. No rockets, no nuclear weapons, no technology capable of altering the path of an object 6 miles wide traveling at 20 kilometers per second. They could only watch and wait, and know that the end was coming, that there was nothing they could do to stop it, or perhaps they had no warning at all. Perhaps the asteroid came from an angle where the sun's glare obscured it until too late. Perhaps their astronomy was not advanced enough to detect small objects. Perhaps the morning of the impact began like any other morning. Dinosaurs going about their lives, unaware that death was minutes away. And then a light in the sky, brighter than anything they had ever seen, growing, coming closer. Some might have pointed, wondered, before the shockwave hit and there was no more time for wondering. Either way, warning or no warning, understanding or confusion, the result was the same: total extinction. And for any civilization that existed, the impact was specifically designed to erase them. Not just kill them, but remove almost every trace. The fires destroyed organic materials. Documents, if they existed, burned. Wooden structures, libraries, anything made from plants consumed in the global conflagration. The tsunamis destroyed coastal settlements. Most civilizations, human and presumably dinosaur, build near water, rivers for transportation and irrigation, coasts for fishing and trade. The waves would have swept away cities if cities existed, carrying the debris far inland or out to sea, scattering it across hundreds of kilometers. The earthquakes collapsed stone structures. The acid rain dissolved exposed minerals and metals, and the burial under meters of impact ejecta covered everything that remained. Then came 66 million years of geological processes finishing what the impact started. The thin layer of debris from the impact, containing whatever traces of civilization might have survived, was buried under kilometer after kilometer of new sediment. Rivers depositing silt, wind carrying dust, ocean currents spreading sediments, each new layer compressing the layers below, heating them, transforming them. Tectonic activity folded the layers, faulted them, thrust some sections upward to be eroded away, and pushed others downward to be melted. Ice ages scraped across the surface. Sea levels rose and fell. Continents moved. The land where the impact occurred, the Yucatan Peninsula, drifted hundreds of kilometers from its original position. And the crater itself, though enormous, was slowly buried and filled until it was invisible from the surface. It was not discovered until 1991, when geologists analyzing gravity and magnetic anomalies noticed a circular pattern buried under the jungle and ocean. The crater had been there all along, hidden, waiting to be found. If cities existed, they met the same fate: destroyed, buried, compressed, transformed, erased. After 66 million years, a city would be unrecognizable. The buildings would be gone, returned to mineral form. The streets would be compressed into thin layers of unusual sediment. Any artifacts, tools, artwork would be corroded, scattered, pulverized. And finding them would require knowing exactly where to look in a specific thin layer of rock that has been buried, folded, and transformed beyond easy recognition. The impact created perfect conditions for obliterating evidence. Not just the direct destruction, but the geological reset that followed, burying everything under new layers, giving time 66 million years to erase what the impact did not destroy immediately. But perhaps some survived, not the civilization. The impact was too thorough for that, but individuals, small groups, in deep caves perhaps, or far from the impact site in isolated regions, with stored food and shelter and luck. They could have survived the initial catastrophe. Survived the fires because they were underground. Survived the cold because they had shelter. Survived the darkness because they had preserved food, dried meat, or stored grains if they had agriculture. They could have emerged after months or years to find a world transformed, the sun returning, but the forests gone. The great herds extinct, the cities, if they had cities, reduced to rubble and ash, and they would face the survival bottleneck problem. A species needs a minimum viable population to avoid extinction. Geneticists estimate that humans would require at least 500 individuals, preferably several thousand, spread across multiple isolated groups to maintain enough genetic diversity to survive long-term. Below that threshold, inbreeding causes genetic problems that accumulate over generations until the species cannot sustain itself. If intelligent dinosaurs survived the impact, scattered in small groups of 10 or 20 individuals in isolated refuges across the planet, they would face this bottleneck. Each group too small to be viable alone, too isolated to interbreed with other groups. And living in a world that no longer supported their way of life. The post-impact world was harsh. For years after the darkness lifted, the climate remained unstable. Food was scarce. Large animals, the easy prey that carnivores depended on, were extinct. Plants were slowly recovering, but not in the abundance that had existed before. Competition for resources was fierce, and intelligent species with their large energy-hungry brains were at a disadvantage. Intelligence is expensive. The human brain consumes 20% of our body's energy despite being only 2% of our mass. A dinosaur with similar brain-to-body ratio would face similar energy costs. In a world of scarcity, that cost might be too high. Evolution would favor smaller, more efficient brains. Less intelligence but better survival. Over thousands of years, the survivors would change, if they survived at all. Natural selection pushing towards smaller bodies, smaller brains, simpler lifestyles. Or they would simply go extinct, populations dwindling generation by generation until the last individual died alone, the final remnant of a species that had once looked at the stars and wondered whether they were alone. And with that death, the knowledge would die too. Because civilization is not just individuals, it is accumulated knowledge, and knowledge requires transmission. Teachers and students, books or oral traditions, stability and time. In a world of scarcity and survival, there was no time for teaching complex mathematics or engineering. There was only time for finding food, avoiding predators, staying alive one more day. The knowledge of how to build, how to create, how to understand the cosmos, all of it would fade within a few generations. First, the theoretical knowledge would go. The mathematics, the astronomy, the abstract sciences, these provide no immediate survival advantage. Parents would not teach them because survival skills were more urgent. Second, the technological knowledge. How to smelt metal, how to build structures, how to create tools. These might persist longer because they have practical applications. But without the infrastructure to support them, without mines and forges and workshops, even practical knowledge becomes useless. You cannot teach metalworking if there is no metal to work. Third, even the memory that civilization existed would fade. By the third or fourth generation, children would hear stories from grandparents about the time before the sky fell, about cities and lights and wonders. But the stories would sound like myths, like fantasies. The children would not believe them because the world they lived in contained nothing that matched those descriptions. And over more generations, even the myths would change. The specifics would be lost. The stories would become about gods and monsters, not ancestors and technology, until finally nothing remained, not even the memory. This is how civilizations disappear completely, not just their buildings and artifacts erased by geological time, but their knowledge erased by catastrophe and the desperate scramble for survival that follows. The asteroid did not just kill the dinosaurs. If they had civilization, it killed civilization itself, shattered it so completely that even if survivors lingered for centuries or millennia afterward, they could never rebuild what had been lost. And 66 million years later, we search the rocks and find nothing because there is nothing left to find. The impact was not just an extinction event. It was an erasure event. A cosmic catastrophe so perfectly timed, so thoroughly destructive, that it ensured any species unlucky enough to be thriving at that moment would be removed from history almost without a trace. And if intelligent dinosaurs existed on that morning 66 million years ago, if they looked up and saw the light growing in the sky, they had only moments to realize that everything they had ever built, everything they had ever known, everything they had ever hoped for was about to end. Not gradually, not with time to prepare or preserve, but in fire and darkness and the silence that follows when a world dies. And then time took what the asteroid left behind and erased even the memory that they had ever existed at all. If we allow ourselves to imagine, just for a moment, that intelligent dinosaurs did exist, that somewhere in the vast expanse of the Cretaceous or Jurassic periods, a species crossed the threshold from animal to civilization builder, what would that civilization have looked like? This is not idle speculation. This is an exercise in understanding what is physically possible, what materials were available, what technologies could be developed with the resources Earth provided during the age of dinosaurs. And the answers might surprise you, because the Earth of 100 million years ago was not some alien world. It was this world, the same physics, the same chemistry, the same raw materials. If humans could figure out metallurgy and agriculture and architecture, there is no reason dinosaurs could not have figured out the same things, maybe differently. Maybe following a path we would not recognize, but the potential was there. The question is not whether it was possible. The question is what form it might have taken. Let us start with energy, because every civilization needs energy. Fire for warmth, for cooking, for working materials. Mechanical power for moving things, for construction, for manufacturing. Humans began with wood, burned it for heat and light, then discovered that burning wood at high temperatures could smelt metals from ore. Later, we discovered coal, fossilized plant matter from the Carboniferous period that burned hotter and longer than wood. Then oil and natural gas, then nuclear power, then renewables, each step expanding what we could do, what we could build, how much energy we could harness. A dinosaur civilization would have had access to most of these same energy sources. Wood was obviously available. The Mesozoic era, the age of dinosaurs, was a time of lush vegetation. Forests covered much of the land. Conifers, cycads, and later flowering plants provided abundant fuel. Discovering fire would be the first step, and there is no reason to think dinosaurs could not make that discovery. Many modern birds, descendants of dinosaurs, are fascinated by fire. Some species in Australia have been observed picking up burning sticks and deliberately carrying them to new locations to flush out prey from the resulting fires. This is not tool use in the traditional sense, but it is fire manipulation. The mental leap from manipulating existing fire to creating fire deliberately is not large. Friction, striking stones together, focusing sunlight through water droplets, any of these methods could work. And once fire is controlled, cooking becomes possible. Cooked food is easier to digest, provides more calories, and reduces the energy cost of digestion. This frees up energy for larger brains. Fire also provides warmth, extends activity into the night with light, and most importantly, enables metallurgy. Coal existed during the dinosaur age. In fact, much of the coal we burn today formed during the Carboniferous period, about 300 million years ago, before dinosaurs even evolved. These coal deposits were accessible on or near the surface in many regions. Erosion would have exposed coal seams. Forest fires burning through coal-rich areas would have demonstrated that this black rock burned hotter and longer than wood. A curious, intelligent species would have noticed, would have experimented, would have realized coal could be mined and used deliberately. Burning coal produces temperatures high enough to smelt copper and tin, the materials needed for bronze. High enough to work iron if you build the right kind of furnace. A dinosaur civilization could absolutely have entered a Bronze Age or Iron Age using coal as their primary fuel source. But there is an alternative that we often overlook because humans did not use it extensively until recently: geothermal energy. The Earth of the dinosaur age was volcanically active, more active than today in many regions. Volcanic zones offered abundant heat just below the surface. Hot springs, geysers, volcanic vents, all providing steady, reliable heat. A civilization that developed near volcanic regions could potentially tap this heat directly. Use it for warming structures, for cooking, for industrial processes. The Romans, thousands of years ago, used geothermal heat for baths and heating buildings. They did not have sophisticated technology, just an understanding that hot water from the ground could be channeled and used. A dinosaur civilization could have done the same, possibly even more extensively. And here is the important part. Geothermal energy leaves almost no trace. It does not create carbon emissions. It does not require mining that leaves obvious scars. A civilization powered primarily by geothermal would be nearly invisible in the geological record. We would never detect it unless we found their structures, and as we have discussed, structures do not survive 66 million years. Agriculture would have been possible, though different from human agriculture. Humans domesticated grasses, wheat, and rice and corn because we are omnivores who can digest grains. Dinosaurs had different dietary needs. Herbivorous dinosaurs could have domesticated the plants they ate. Cycads, ferns, conifers, selected for varieties that grew faster, produced more edible material, were easier to harvest. There is evidence some dinosaurs engaged in what might have been early agriculture even without intelligence. Fossilized trackways show that some herbivore species returned repeatedly to the same feeding grounds. trampling the soil in ways that would have planted seeds and fertilized the ground with their dung. This is not intentional agriculture, but it is the beginning. The step from accidentally encouraging plant growth to deliberately planting and tending crops is not large. Carnivorous dinosaurs could have domesticated prey species. Humans domesticated cattle, pigs, chickens. Dinosaurs could have domesticated smaller herbivorous dinosaurs, keeping them in herds, protecting them from other predators, selectively breeding them for size or docility or meat production. The intelligence required for animal husbandry is well within the range of what modern birds demonstrate. Crows understand delayed gratification, the concept of investing effort now for greater reward later. That is exactly the mental framework needed for agriculture and herding. You plant seeds and wait for harvest. You protect young animals and wait for them to grow. Intelligence plus patience equals agriculture. With surplus food from agriculture comes specialization. Not everyone needs to hunt or gather. Some can become craftspeople, builders, thinkers. This is how human civilization developed. There is no reason dinosaur civilization could not follow a similar path. Picture a settlement near a river in what is now China or North America 120 million years ago. Several hundred individuals living in permanent structures, some tending crops of ferns and cycads, others managing herds of small ornithopods, herbivorous dinosaurs kept for meat, craftspeople working with stone, bone, and wood to create tools, builders constructing shelters from available materials, and perhaps at the center of the settlement a structure different from the others, larger, more carefully built, a place for gathering, for teaching the young, for storing knowledge. Not a temple necessarily, not a palace, but a communal space that represents the shift from mere survival to actual society. What would their buildings look like? This depends on available materials and environmental needs. Dinosaurs, being reptilian or proto-avian, probably preferred warmth. Their cities might cluster in tropical or subtropical regions where temperatures stayed comfortable year-round. In these climates, shelter from rain and sun is more important than insulation from cold. Structures could be relatively simple: wooden frames covered with thatch or large leaves, stone foundations to elevate buildings above flooding and provide stability. Some dinosaurs were quite large even among intelligent species, so doorways and ceilings would need to be taller than human structures. But the basic principles of architecture are universal: walls to define space, roofs to shed rain, openings for light and air, support structures that distribute weight to foundations. Stone would be their most durable building material. Limestone, sandstone, granite, all available and workable with stone or bronze tools. Cutting stone is labor-intensive but not technologically complex. Humans built the pyramids with copper and bronze tools, ramps, and enormous amounts of organized labor. Dinosaurs could do the same. The difference is that after 66 million years, even stone structures are eroded beyond recognition unless they were massive. And massive structures require significant population and organization. A city of a few thousand could build temples or monuments that might leave some trace. But a village of a few hundred would build smaller, and those structures would be completely gone. Metallurgy is where things get interesting. Working metal requires understanding chemistry, even if you do not call it chemistry. You need to recognize that certain rocks, when heated, produce metal. You need to control temperature precisely to smelt without burning away the metal. You need to understand alloying, mixing copper and tin to make bronze, adding carbon to iron to make steel. These are not obvious discoveries. Humans took thousands of years to progress from copper to bronze to iron, but the knowledge is repeatable. Once you understand the principles, you can teach them, refine them, improve them. A dinosaur civilization could absolutely have developed metallurgy. And once you have metal tools, everything becomes easier. Metal axes for cutting wood, metal plows for agriculture, metal weapons for hunting and defense, metal fittings for construction. The evidence of metallurgy, however, would be nearly impossible to detect after 66 million years. Metal corrodes. Bronze oxidizes into green copper compounds that eventually disperse into the soil. Iron rusts back into iron oxide, indistinguishable from natural iron ore. Even unusual concentrations of metals in specific locations could be explained by natural hydrothermal processes or erosion. You cannot point to a patch of copper-rich soil and declare it evidence of ancient smelting. You would need multiple lines of evidence. Slag, the waste product of smelting, has a distinctive chemical composition, but slag is also a form of rock, and after millions of years it weathers and disperses like any other rock. Finding it would require luck and knowing what to look for. Could they have developed writing? This is a critical question because writing is what allows knowledge to accumulate across generations at scale. Oral tradition works for some things: stories, songs, practical skills. But complex mathematics, detailed astronomical observations, historical records, these benefit enormously from writing. Humans invented writing independently multiple times. Sumeria, Egypt, China, Mesoamerica, all developed writing systems without contact with each other. This suggests writing is not wildly improbable. It is a natural solution to the problem of storing and transmitting information. But writing requires a medium. Humans wrote on clay tablets, papyrus, parchment, paper. Clay tablets can be fired and become ceramics, which are durable. But after 66 million years, even fired ceramics weather away or become indistinguishable from natural clay deposits. Papyrus, parchment, and paper are organic. They decay in centuries, not millions of years. Unless preserved in extraordinary conditions like the Dead Sea Scrolls in desert caves, organic writing materials do not survive deep time. Could dinosaurs have used alternative writing materials? Carved stone like Egyptian hieroglyphs? Possibly, but stone carvings erode. Wind and rain wear away the surface at roughly 1 millimeter per 1,000 years. After 66 million years, even deep carvings would be smoothed away or would look like natural weathering patterns. Metal plates, those corrode as we discussed. Fired clay weathers away. The sad reality is that writing, one of the key markers of civilization, leaves almost no trace after sufficient time unless you bury it in conditions that prevent weathering and are lucky enough that it is never destroyed by tectonic activity or erosion. What about technology beyond basic metallurgy and agriculture? Could dinosaurs have discovered electricity? This seems far-fetched but is not impossible. Electricity can be generated with magnets and coils of wire, or with chemical batteries. The Baghdad battery, discovered in Iraq and dating to around 200 BC, may have been a primitive battery made from a clay jar, copper cylinder, and iron rod. If ancient humans could stumble upon electrochemistry, dinosaurs could too. But building devices that use electricity requires understanding electromagnetism, which requires systematic experimentation and mathematical framework. Not impossible, but it requires a level of scientific method and knowledge transmission that is difficult to achieve without writing and institutional knowledge. Possible, yes, likely in the time span available. Uncertain. What about a completely different technology path? We assume technology looks like our technology. Metal tools, combustion engines, electronics. But what if intelligence takes different forms? What if a dinosaur civilization focused on bioengineering instead of mechanical engineering? Humans are only now beginning to understand genetics and biological manipulation. But the natural world has been doing it for billions of years. Evolution is biological engineering, selection, mutation, adaptation. An intelligent species could harness these processes deliberately. Selective breeding taken to extreme levels, domesticating not just animals for food but organisms for specific purposes. Bacteria that produce light instead of building lamps, fungi that break down waste, plants engineered to grow in specific shapes for construction. Living structures instead of built ones. This sounds like science fiction, but it is within the realm of biological possibility. Modern humans have created glow-in-the-dark fish by inserting jellyfish genes. We have bacteria that produce insulin. We have plants modified to resist pests. A civilization with tens of thousands of years to experiment could go much further. And the beauty of biotechnology is that it leaves almost zero trace. Living things die and decay. Engineered organisms either die out or breed back to wild type within generations if not maintained. After 66 million years, there would be nothing to find. Not even chemical signatures, just normal biological degradation. This possibility is both fascinating and frustrating. Fascinating because it suggests intelligence could take wildly different forms than we imagine. Frustrating because it means even if dinosaur civilization existed and was highly advanced in bioengineering, we would have no way to detect it. We look for metal and concrete and plastics because that is what we made. We might be completely blind to evidence of a civilization that worked with life instead of minerals. How advanced could they have become? If an intelligent dinosaur species arose 100 million years ago and lasted even 1 million years before going extinct naturally or from the asteroid, they would have had roughly 100 times longer than human industrial civilization has existed. We went from the first steam engines to the internet in 300 years. What could a species do with 1 million years? The question becomes almost meaningless because the timescales are so vast. They could have achieved things we cannot imagine, or they could have plateaued at a Bronze Age level for hundreds of thousands of years if environmental or cultural factors prevented further development. Or they could have followed a completely different path, developing deep understanding of biology and ecology while never discovering electronics or spaceflight. The one thing we can say with confidence is that if they achieved space travel and left artifacts on the Moon or Mars, those artifacts would still be there. The Moon has no atmosphere, no erosion, no tectonic activity. A structure on the Moon could survive for billions of years. Mars has thin atmosphere and slow geological processes. Artifacts there could survive for hundreds of millions of years. So far, we have found nothing on the Moon except our own landers and flags. Mars rovers have found no ruins, but we have explored only the tiniest fraction of the lunar and Martian surfaces. And we have not been looking for evidence of previous civilizations. We have been looking for water, for minerals, for signs of microbial life. If we wanted to search properly for dinosaur artifacts on the Moon, we would need systematic surveys of the surface with high-resolution imaging, followed by targeted exploration of anomalies. That has not happened. Maybe it should. Imagine a settlement on the coast of the Tethys Sea, the ancient ocean that separated the northern and southern continents 95 million years ago. A city of perhaps 10,000 individuals. Intelligent theropods descended from Troodon-like ancestors. They have mastered agriculture, growing crops of ferns and primitive flowering plants. They have domesticated smaller dinosaurs for food and labor. They have developed bronze metallurgy, smelting copper and tin into tools and decorative objects. They have built structures from stone and wood, carefully fitted together, housing families in communal spaces. They have a writing system, pictographic, inscribed on clay tablets that are fired for preservation. They have begun mapping the stars, recognizing patterns, tracking the movements of planets. They have oral traditions going back thousands of years, stories of ancestors and the creation of the world. They have art, carvings, and paintings depicting their gods and heroes. They have music, instruments made from bone and wood. They have mathematics enough to build their structures and predict astronomical events. They have medicine, understanding which plants help with illness and which are dangerous. They have trade routes connecting their city to others hundreds of kilometers away. They have social hierarchy, leaders and followers, specialists and laborers. They are a civilization. Not as technologically advanced as modern humans, but more advanced than any human society before 3000 BC. And they have existed for 50,000 years, slowly developing, slowly growing, passing knowledge from generation to generation. They believe they will last forever. They cannot imagine their world ending. And then one night an astronomer notices something strange, a new star in the sky, except it is not a star. It is moving. Getting brighter night by night, something is approaching, something from the void. They do not understand what it means. They have no framework for comprehending asteroids or cosmic impacts. Some are fright, some think it is a god approaching, some think it is a sign, and the light grows brighter. Until that morning, until the sky splits, until the world ends in fire, and everything they built, everything they knew, everything they were is erased. This is speculation, complete speculation, but it is plausible speculation. Nothing in this scenario violates physics or biology. Nothing requires magic or impossible technology. It is simply asking, if the ingredients were present, if intelligence evolved, what might have happened? And the answer is something like this. Maybe not exactly this. Maybe differently organized, maybe different technologies, maybe different timescales, but something that we will never find because time and catastrophe erased it so thoroughly that not even legends remain. Just the question, just the wondering, just the faint possibility that we are not the first to look at the stars and ask whether we are alone in the universe. That the answer echoing back across 66 million years of silence might be no, you are not alone, others were here. Others wondered, others built and dreamed and were forgotten. And the cycle, perhaps, is older than we ever imagined. The question of who built and what they built remains unanswered. But the possibility that they built at all, that intelligence is not a recent invention but an ancient pattern repeating across deep time, that possibility cannot be dismissed. And that changes everything about how we see ourselves and our place in the long, strange, tragic story of life on Earth. There is a particular kind of frustration that comes from asking a question that might be unanswerable. Not because the answer does not exist, but because time has destroyed the evidence beyond any hope of recovery. We live in an age where we can sequence DNA from 40,000-year-old Neanderthal bones, where we can detect planets orbiting stars thousands of light years away, where we can measure the temperature of the universe 13 billion years ago by studying the cosmic background radiation. But we cannot tell you with certainty whether an industrial civilization existed on this planet 66 million years ago, not because we lack technology, but because we have barely looked, because the sample size is laughably small, because institutional science does not fund searches for things the paradigm says do not exist, and because even if we wanted to look properly, even if we devoted resources to systematic searching, the odds of finding definitive proof are vanishingly small. This is the reality we must confront. The question of dinosaur civilization might be permanently unanswerable, and we need to make peace with that uncertainty. Let us talk about sample size. This is not abstract statistics. This is the fundamental problem that makes the Silurian hypothesis so difficult to test. Earth's sedimentary rock record, the layers of compressed sediment where fossils and chemical traces might be preserved, represents billions of years of deposition. The total volume is almost incomprehensible. Sedimentary rocks cover approximately 73% of Earth's land surface and most of the ocean floor. The average thickness of sedimentary layers on continents is about 1/8 kilometers. On ocean basins, much thicker in some places. Do the math. Multiply surface area by thickness. You get a volume measured in hundreds of millions of cubic kilometers. That is the haystack, and we are looking for needles, chemical anomalies, unusual isotope ratios, traces of synthetic molecules, concentrated rare earth elements. These would be scattered through tiny, thin layers representing perhaps a few thousand years of deposition during whatever period a civilization existed. Layers that might be only millimeters thick after geological compression. Now ask yourself, how much of this vast volume have we actually examined? The answer is shocking. Less than 1/100th of 1%, probably less than 1,000th of 1%. Most sedimentary rock is buried deep underground or under the ocean, completely inaccessible without drilling. And drilling is expensive. A deep geological core might cost hundreds of thousands of dollars. The deepest drilling project ever, the Kola Superdeep borehole in Russia, took 20 years and reached just 12 kilometers depth. It was a monumental scientific achievement. And it sampled one tiny vertical slice through the crust in one location. One out of millions of potential locations, out of billions of potential sample sites. Most drilling is done for practical purposes, looking for oil, looking for natural gas, looking for minerals, looking for geothermal energy, looking for groundwater. These drillers pull up core samples, examine them for the specific thing they are looking for, and discard or archive the rest. Climate scientists retrieve cores from ocean floors and ice sheets to study past climate. They analyze isotope ratios, but they are looking for climate signals, temperature proxies, atmospheric composition, not industrial signatures from civilizations that might have existed tens of millions of years ago. Paleontologists occasionally drill or excavate when they find fossil-bearing layers, but they are looking for bones, for preserved organisms, not for chemical anomalies that might indicate technology. In other words, we have examined a tiny fraction of Earth's geological record, and within that tiny fraction, we have been looking for specific things that have nothing to do with detecting ancient civilizations. It is like searching for a particular book in a library the size of North America by randomly opening 5 books and glancing at one page in each. Finding nothing, you conclude the book you want does not exist anywhere in the library. This is not rigorous. This is not scientific certainty. This is assumption based on grossly insufficient data, but it gets worse. Even the rock we have examined is not from the right time periods or the right places. The Cretaceous period, when dinosaurs thrived, lasted from about 145 to 66 million years ago. That is 79 million years of Earth history. Rocks from this period exist, obviously, but many are buried. Many have been metamorphosed by heat and pressure, transforming them into types of rock that no longer preserve fine chemical details. Many have been subducted into the mantle and destroyed. Many are in locations we cannot access, under cities or oceans or politically restricted areas. The exposed, accessible, well-preserved Cretaceous sediments that we have studied in detail represent perhaps a few 10,000ths of all Cretaceous sediments that ever existed. And we have analyzed those for dinosaur fossils, for climate proxies, for understanding mass extinction. Not for plutonium-244, not for synthetic molecule fragments, not for industrial chemical signature, because nobody funds that research, because the paradigm says it would be a waste of money. This brings us to paradigm protection, one of the most powerful forces in science, not a conspiracy, not deliberate suppression of truth, but something more subtle and more pervasive. The scientific method works through hypotheses. You propose something might be true, design experiments to test it, analyze results, draw conclusions. But if the dominant paradigm says something cannot be true, nobody proposes the hypothesis. Nobody designs the experiments. Nobody asks for funding. And funding committees, composed of scientists who were trained in the paradigm, reject proposals that challenge it as fringe or pseudoscience. This is not malicious. This is conservative scientific practice. Most wild hypotheses are wrong. Most challenges to established theory are based on misunderstandings or errors. So scientific institutions have built-in resistance to change. This resistance protects against false ideas, but also slows acceptance of genuinely new discoveries. The paradigm regarding human uniqueness is particularly strong. We are taught from childhood that humans are special. The only intelligent species Earth has produced. The pinnacle of evolution. This belief is reinforced by religion, by philosophy, by cultural narratives about human exceptionalism. Challenging it feels threatening, not just scientifically but existentially. If we are not unique, if intelligence evolved before and went extinct, what does that say about our future? What does that say about the meaning of our achievements? These are uncomfortable questions, and science, despite its ideals of objectivity, is practiced by humans with human psychological needs. We resist ideas that threaten our sense of importance. So when Frank and Schmidt published the Silurian hypothesis, the response from most scientists was polite dismissal. Interesting thought experiment, useful for thinking about biosignatures on exoplanets, but not a serious proposal for actual research. The paper was not rejected or attacked. It was simply not taken seriously enough to inspire follow-up funding. No major geological surveys were initiated to search for industrial chemical signatures in Cretaceous sediments. No systematic screening for plutonium-244 or synthetic molecules. No coordinated effort to sample globally and comprehensively. Because the paradigm says dinosaurs were not intelligent, therefore no civilization existed, therefore no point looking. The conclusion is assumed, not tested. But what if the paradigm is wrong? What if absence of evidence in a situation where evidence would be nearly impossible to find anyway has been mistaken for evidence of absence? This is the trap. Science requires falsifiability. A hypothesis must be testable. The Silurian hypothesis appears unfalsifiable because proving a negative, proving something did not exist, is nearly impossible when evidence degrades over deep time. But actually it is falsifiable in one direction. Finding definitive evidence like plutonium-244 in Cretaceous sediments would prove industrial civilization existed. Not finding it proves nothing because we have barely looked and evidence might not have survived. This asymmetry is frustrating. But it is the reality of investigating deep time. Now imagine just for a moment that tomorrow geologists announce a discovery. A sediment core from an ancient lake bed in what is now Mongolia. Cretaceous age, 95 million years old. The core shows a thin layer just 5 millimeters thick with unusual chemical signatures. Carbon isotope ratios indicating massive fossil fuel burning. Nitrogen isotope shifts suggesting fertilizer use. Concentrated neodymium and dysprosium, rare earth elements in ratios that do not match any known natural process. And most stunning of all, traces of plutonium-244, not much, parts per trillion, but unmistakably there. Multiple labs confirm. Independent samples from the same layer and other locations show the same signatures. The scientific community is in shock. What would happen? First, denial, claims of contamination, modern plutonium from nuclear testing somehow infiltrating the samples, even though the samples came from hundreds of meters underground in undisturbed sediment, even though contamination should show in surrounding layers but does not. The cognitive dissonance would be enormous. Everything we believe about being first, about human uniqueness, about the timeline of intelligence on Earth would be challenged. Some scientists would embrace the evidence, would begin searching for more, would propose new frameworks for understanding the rise and fall of civilizations across deep time. But many, perhaps most, would resist, would demand more evidence, would argue the findings could be explained by unknown natural processes. Would protect the paradigm because paradigms do not fall easily. Peer review would become a battlefield. Papers presenting the evidence would be subjected to extreme scrutiny. Reviewers would demand explanations for every anomaly, every uncertainty. Standards of proof would be raised higher than for any conventional discovery, and media coverage would be chaotic, sensational headlines. Dinosaur cities found, even though no cities were found, only chemical traces. Conspiracy theory, government knew all along. Religious debates, does this disprove creation? Public confusion, what does this mean? Are we descended from dinosaurs? Did they visit aliens? The signal would be lost in noise. Educational institutions would be slow to respond. Textbooks take years to revise. Teachers would be uncertain how to present the information. Does this go in biology class, history, earth science? And what do we tell students about human uniqueness if we are not actually unique? The cultural shift would take generations. Because this is not just about dinosaurs, this is about identity, about how we understand ourselves in the cosmic context, about whether we are special or just latest in a long line of experiments, most of which failed. But here is the hard truth. That announcement is probably never coming, not because evidence does not exist, but because finding it would require a coordinated effort that nobody is funding. It would require systematic sampling of Cretaceous sediments from dozens or hundreds of locations worldwide. It would require developing new analytical techniques to detect degraded chemical signatures. It would require screening for elements and molecules we are not currently looking for. The cost would be at least $50 to $100 million over 10 years, maybe more. And funding committees would ask the reasonable question: what is the probability this search succeeds? And the honest answer is very low. Not because civilizations did not exist, but because evidence degrades, because sample sizes are small, because 66 million years is a long time, and very low probability of success means funding goes to other projects with higher expected returns. So we are left with uncertainty, permanent, frustrating uncertainty. We cannot prove dinosaur civilizations existed. We also cannot prove they did not exist. The question hangs in limbo, unanswered and probably unanswerable with current resources and scientific priorities. Some people find this intolerable. They want definitive answers, yes or no, but science does not always provide closure. Sometimes the honest answer is, we do not know, we cannot know. The evidence has been destroyed by time, and we must learn to live with that ambiguity. There is, however, value in asking the question even without answering it. The Silurian hypothesis does something important. It challenges assumption. It makes us examine why we believe we are first. It forces us to confront the limits of geological preservation. It teaches us humility about what we can know and what is forever lost to time. It prepares us for searching for signs of intelligence on other planets by making us think about what traces persist and what vanish. And it gives us perspective on our own civilization. Because if dinosaurs could rise and fall and be forgotten, so can we. This is not abstract philosophy. This is concrete possibility. 66 million years from now, if an intelligent species evolves on Earth, what will they find of us? They will find a thin layer of sediment with unusual chemistry, carbon spike from fossil fuel burning, plastic microparticle concentrations, elevated levels of certain metals from industrial pollution, possibly plutonium and other artificial isotopes from nuclear testing, though most will have decayed by then. Possibly fragments of synthetic molecules in especially well-preserved sediments, and they will debate. Some will say this was an industrial civilization. The signatures are clear. Others will say these anomalies can be explained by natural processes, volcanic eruptions, unusual tectonic events. We cannot be sure. And they will be right to be uncertain, because after 66 million years, certainty becomes impossible. The evidence degrades, the traces blur, and the question of whether we existed as a civilization or just as another animal species becomes genuinely difficult to answer. This should terrify us. Not because we want to be remembered, though perhaps we do, but because it means everything we build, everything we create, everything we think is important and permanent is actually fragile and temporary. The buildings will crumble, the art will decay, the books will rot, the digital information will be lost when the storage media fails and the knowledge of how to read it disappears. Within thousands of years, most traces of our civilization will be gone. Within millions, almost nothing identifiable remains. We think of ourselves as builders of permanent things, but on geological timescales, we're building sandcastles at the edge of a tide that is already coming in. And if we accept this, if we truly internalize that we could be forgotten as completely as any dinosaur civilization might have been forgotten, it changes how we think about legacy. Maybe legacy is not about physical monuments. Maybe it is not about leaving traces that last forever. Maybe legacy is about what we do for the generations immediately after us, how we treat the planet we will pass to our children, what knowledge we preserve for them in forms they can access and use, whether we create conditions for them to thrive or to struggle. Deep time may forget us. But the next few centuries will not, and that is where our responsibility lies. The question of whether dinosaurs built civilizations is probably unanswerable. The evidence, if it ever existed, is degraded beyond recovery. The sample size is too small. The funding does not exist. The paradigm resists. We are left with possibility, not proof, with imagination, not certainty, with questions that echo into the void without returning answers. And maybe that is okay. Maybe not every question needs an answer. Maybe some mysteries are meant to remain mysteries, but asking the question has value. It expands our thinking, it challenges our assumptions, it humbles our certainty, and it reminds us that we are part of a story much longer and stranger than we usually acknowledge. Somewhere buried in rock layers we will never examine, there might be a chemical signature, a thin line of unusual isotopes, a concentration of rare elements, a trace of something that should not be there naturally. And if we found it, if we looked in the right place at the right time with the right equipment, we might glimpse the shadow of minds that existed before us. Minds that wondered and built and ultimately disappeared into the silence. Or we might find nothing, because nothing is there. Because civilizations never arose because we truly are first. Both possibilities are unsettling, both change how we see ourselves, and not knowing which is true is the space we must learn to inhabit, the space of permanent uncertainty, the space where questions live without answers. The space where the only honest statement is, we do not know, we cannot know. And we must proceed anyway, must build our own civilization knowing it will not last forever, knowing it might be forgot, knowing that 66 million years from now some other species might be asking whether we existed, and they will not be certain either, and the cycle continues, intelligence emerging, wondering, building, disappearing, and time erasing almost everything, almost, but not quite. Leaving just enough uncertainty to keep the question alive, just enough possibility to make the search worthwhile, just enough mystery to remind us that the universe does not owe us answers. It only offers questions, and the courage to ask them is what makes us human. Or perhaps what made the dinosaurs more than reptiles. If they existed, if they wondered, if they asked, we will probably never know, but the asking itself is enough. If intelligent dinosaurs really did exist, if somewhere in Earth's deep past a thinking species rose, built, wondered, and vanished, then this is not just a story about them. It is a story about us. Because the most important lesson of the Silurian hypothesis is not whether dinosaurs had cities. It is what their possible disappearance tells us about the fate of intelligence itself, about the fragility of civilizations, about how easily thinking minds can vanish from the universe without leaving more than a whisper in stone. We like to believe that intelligence is a kind of shield, that being smart makes us safer. That our technology, our knowledge, our planning give us control over the future. But the dinosaurs, if they built a civilization, would prove something deeply unsettling. Intelligence does not guarantee survival. It never has. For 165 million years, dinosaurs dominated Earth. That is an almost unimaginable span of time. Human civilization, by comparison, is a heartbeat. 10,000 years since agriculture. 300 years since industrialization. In geological terms, we are barely here. And yet, in those 300 years, we have altered Earth's climate, changed atmospheric chemistry, driven countless species to extinction, and built technologies capable of destroying ourselves many times over. The dinosaurs, if intelligent, were wiped out by an external force. A random cosmic accident, a rock falling from space. They had no control, no choice, no way to stop it. We are different. Our greatest threats today are not asteroids, they are ourselves. Climate change is not a mystery to us. We understand the physics, we know the cause, we know the consequences. Nuclear weapons are not myths, they exist. Thousands of them. Artificial intelligence is not science fiction. It is developing now, faster than social systems can adapt. Biological weapons, ecological collapse, runaway technological risks, these are dangers created by intelligence itself. The terrifying possibility is this: intelligence might not be a stable evolutionary strategy. It might be a temporary phase. A brief moment where a species becomes smart enough to reshape its environment, but not wise enough to survive the consequences. If dinosaurs had intelligence and lost it all, then intelligence is not rare, but long-term survival might be. Consider the numbers again. Dinosaurs ruled for 165 million years. Humans have had industrial civilization for 300. That means dinosaurs lasted 550,000 times longer than our industrial era has existed so far. And yet they are gone, completely, erased so thoroughly that we cannot even be sure they ever thought at all. This should force us to ask a painful question. Are we any different? We often assume that our future stretches endlessly forward. That technology will solve our problems. That progress is inevitable. But history, both human history and deep evolutionary history, tells a different story. Civilizations rise, civilizations fall, knowledge accumulates then fragments, skills are lost, stories become myths, and eventually nothing remains but traces too faint to interpret. If humans were to disappear tomorrow, not all life, just us, what would remain? Cities would crumble within centuries, steel would rust, concrete would fracture and erode. Digital data would vanish almost immediately without electricity and maintenance. Within 10,000 years, our world would look wild again. Forests growing through streets, animals reclaiming land. And within a few million years, almost nothing would suggest a global technological civilization ever existed. 66 million years from now, future geologists might drill into Earth's crust and find a thin, strange layer. A sudden carbon isotope spike, plastic microparticles, unusual metal concentrations, maybe traces of artificial radioisotopes, and they would argue, some would say this was an industrial civilization. Others would say natural processes can explain this, and the truth would be ambiguous, exactly like the debate we are having now. This is the mirror the Silurian hypothesis holds up to us. We are not just asking whether dinosaurs were intelligent. We are rehearsing how future beings might question our own existence. And that leads to an uncomfortable realization. If we want to be remembered not in myth, not in speculation, but in certainty, then doing nothing is not enough. Geological time is ruthless. It erases almost everything. So what could survive? One answer is space. The moon has no atmosphere, no erosion, no plate tectonics. Footprints left there today will last millions of years, possibly billions. Artifacts placed on the moon could outlive Earth itself. A simple plaque, a carved message, a sealed archive, these would survive longer than any monument on Earth. Mars, too, offers partial preservation. Its thin atmosphere and slow geology mean structures could last far longer than on Earth. If we ever build there, we will be leaving marks that may persist long after our species is gone. Another answer lies deep underground. Certain stable geological formations, ancient cratons billions of years old, experience almost no tectonic activity. Burying intentional markers there, synthetic minerals, long-lived isotopes, encoded information, could preserve evidence of our existence far into the future. There is also a more radical idea, biological memory. Information stored in DNA. Encoded messages inside extremophile organisms designed to survive extreme heat, pressure, radiation. Life itself as an archive. This may sound strange, but biology has proven to be one of the most durable information storage systems ever discovered. DNA has survived hundreds of millions of years in fossilized fragments. With intention, it could survive much longer. But here is the deeper question. Should we care? Does it matter if we are remembered by some distant intelligence millions of years from now? From a personal perspective, maybe not. None of us will be there, but from a species perspective, remembrance is not about ego. It is about continuity, about passing knowledge forward, about not forcing future intelligence to wonder blindly the way we are wondering now. If dinosaurs were intelligent and we never knew, then something precious was lost. Not just them, but the knowledge that intelligence had already walked this path before. Do we want to be that mystery for someone else? There is another lesson here, quieter but just as important. If intelligence has appeared before and vanished, then we are not the center of the story. We are a chapter, maybe not the first, almost certainly not the last. And that can be terrifying, but it can also be liberating. We do not have to be perfect. We do not have to be eternal. But we do have a responsibility to ourselves, to future life, to the planet that made us. Because if dinosaurs built a civilization and lost it all, then the real question is not were they intelligent. The real question is, what did they lack that we might still develop? Wisdom, long-term thinking, restraint, a sense of responsibility beyond immediate survival and expansion. The asteroid was random, we are not. Our extinction, if it comes, will likely be self-inflicted. And that makes all the difference. The Silurian hypothesis is not a warning carved in stone. It is a whisper from deep time, a reminder that intelligence alone is not enough, that survival requires humility, that civilizations are fragile, that the universe does not guarantee second chances. Somewhere beneath our feet, in rocks billions of years old, there may be traces of minds that once wondered what we are wondering now. And one day, if we fail, there will be traces of us too. Thin, ambiguous, debated. The question is not whether we will be remembered. The question is whether we will learn. At the end of every long journey through time, there is a moment of silence, a pause, a breath. We have traveled hundreds of millions of years into Earth's past. We have imagined worlds that no human ever saw. Creatures that lived, hunted, raised their young, and died long before the first human heart ever beat. We have followed a question that began as a scientific thought experiment and slowly unfolded into something far larger, something more unsettling than we expected. And now, at the very end of this journey, we arrive not at an answer but at a mystery. Because the deepest truth of all this is simple and yet profoundly uncomfortable. We do not know. We do not know whether intelligent dinosaurs ever existed. We do not know whether cities rose beneath alien stars of the Mesozoic sky. We do not know whether minds once looked at the universe from reptilian eyes and asked the same questions we ask today. And perhaps most unsettling of all, we may never know. Science is powerful, but it is not omnipotent. It is a method, not a time machine. It works with evidence, and evidence does not always survive. Over deep time, truth erodes, certainty dissolves. The universe keeps its secrets not because it is cruel, but because time is indifferent. 66 million years is not just a long time. It is long enough for continents to wander across the planet, long enough for oceans to open and close, long enough for mountains to rise and be ground back into dust, long enough for entire evolutionary experiments to appear, flourish, and vanish without leaving more than a faint chemical whisper behind. If intelligent dinosaurs existed, their story is now written in a language we barely understand. A language of isotopes, sediments, and anomalies so subtle they can be dismissed as noise. Their monuments, if they ever stood, are now indistinguishable from hills. Their tools, if they ever shaped them, are now just minerals scattered through rock. Their words, if they ever spoke or wrote them, dissolved into silence tens of millions of years ago. And so we stand at the edge of knowledge, staring into a darkness that science cannot fully illuminate. This is where many people become uncomfortable. We are used to answers. We crave conclusions. We want certainty, but deep time does not offer closure. It offers perspective. To understand how fragile certainty becomes, imagine holding a piece of Cretaceous rock in your hand. 95 million years old. This rock was once mud at the bottom of an ancient lake. It settled slowly, grain by grain, as dinosaurs walked along the shoreline. It contains minerals, maybe a fossil fragment, maybe pollen from plants that no longer exist. But what else might it contain? A trace of industrial smoke captured in carbon ratios, a hint of unusual chemistry from ancient metallurgy, a whisper of something artificial or something that only looks artificial to us. Without context, without expectation, without knowing what to search for, that rock tells no story. It is silent, not because nothing happened, but because we do not know how to listen. This is the final irony of the Silurian hypothesis. If a civilization existed deep in Earth's past, it could be invisible not because it was small or primitive, but because time is extraordinarily efficient at erasing complexity. The more complex something is, the more fragile it becomes. Knowledge requires minds to hold it. Technology requires maintenance. Civilization requires continuity. Break that continuity and everything collapses. The asteroid did not just kill the dinosaurs. It broke the chain of memory. It shattered the delicate network of teaching, learning, and cultural transmission that makes civilization possible. And once that network is gone, recovery becomes nearly impossible. This is not just speculation. We see it in human history. When civilizations collapse through war, famine, disease, or environmental change, knowledge disappears astonishingly fast. Writing systems are forgotten, engineering techniques vanish, technologies regress. Within a few generations, what was once obvious becomes mythical. Within a few centuries, it becomes legend. And given enough time, even legends fade. Now stretch that process over millions of years. If even a handful of intelligent dinosaurs survived the impact, scattered across a ruined world, they would not rebuild civilization. Not because they lacked intelligence, but because civilization is a collective phenomenon. It requires numbers, stability, and time. Without those, intelligence becomes a tool for survival, not for progress. And survival in a post-apocalyptic world favors simplicity, smaller body, lower energy demands, shorter lifespans, less cognitive overhead. Natural selection would not reward philosophers in the ashes of a dead world. It would reward those who could endure hunger, cold, and scarcity. Intelligence would become a liability, and slowly, generation by generation, it would be selected against. This may be the darkest implication of all. Intelligence might not be the destination of evolution. It might be a phase. A brief window where a species becomes aware enough to reshape its environment, and then either learns restraint or destroys the conditions that made intelligence possible in the first place. If dinosaurs crossed that threshold and failed, then their story is not a curiosity. It is a warning written in stone. And now, inevitably, the mirror turns fully toward us. Imagine Earth 66 million years from now. Not as it is today, but as it will be after humanity is long gone, whether through extinction, transformation, or something we cannot yet imagine. A new intelligent species evolves, perhaps descended from birds or rodents or octopi or something entirely unfamiliar. They develop science. They study geology, they drill into ancient rock layer, and they find something strange. A thin layer almost insignificant, a sudden spike in carbon isotopes, microplastics embedded in sediment, unusual concentrations of metal, a brief pulse of radioactive elements. They debate, some say this was an industrial civilization. Others argue natural processes can explain these anomalies. Funding is scarce, evidence is ambiguous, consensus never fully forms. Sound familiar? They might argue for centuries about whether humans were intelligent, whether we built cities or were simply another species that briefly altered the planet, whether our ruins were real or imagined. And they would be right to argue, because deep time makes certainty impossible. This is the most haunting realization of all. We are not just studying the past, we are rehearsing how we will be forgot. And this realization can feel heavy, even depressing, but it does not have to be, because there is another way to see this story. If intelligence has arisen before, whether in dinosaurs or not, then intelligence is not a miracle. It is not unique, it is not sacred, it is something the universe does given enough time and the right conditions. And that is beautiful. It means we are not alone in time. It means consciousness is not a fluke. It means the universe is capable of knowing itself again and again. But it also means intelligence is fragile. It does not automatically persist. It does not guarantee survival. It must be protected, guided, and restrained. If dinosaurs were intelligent and vanished, they are not a failure. They are part of a pattern of emergence, exploration, and disappearance. And we are part of that pattern now. The final mystery then is not whether dinosaurs built cities. The final mystery is whether intelligence can ever truly learn from its own past, especially when that past has been erased. Can a species become wise enough to survive itself? Can knowledge be preserved across catastrophes? Can civilization learn to think in millions of years instead of election cycles and lifetimes? These questions have no easy answers, perhaps no answers at all. And yet, asking them matters, because asking questions is what intelligence does. Somewhere long ago, perhaps a dinosaur stood beneath a strange sky and wondered. Perhaps they asked where they came from. Perhaps they told stories about the stars. Perhaps they worried about the future, or perhaps they never existed at all. And that uncertainty, that unresolved possibility is the point. The universe does not give us neat narratives. It gives us fragments, hints, shadow, and invites us to think carefully about what they mean. we began this journey with a simple question. What if dinosaurs built a civilization before humans existed? We end it not with an answer but with a deeper understanding. That time erases almost everything. That intelligence is rare but not guaranteed to last. That certainty is a luxury of the present moment. And that our story, like all stories, will one day be incomplete. Perhaps that should make us humble. Perhaps it should make us careful. Perhaps it should make us grateful for this brief moment where we get to think, to wonder, to ask questions into the dark. Because whether or not dinosaurs ever asked them before us, we are asking them now. And that, for now, is enough. Thank you for watching. If this journey through deep time made you think, if it left you with questions rather than answers, consider subscribing for more stories like this, where science meets mystery and the past reflects quietly back at us.